Today's question is, light crosses the entire universe, yet for light itself, no time passes. How is that even possible? In simple terms, why doesn't light experience time? I want to talk to you today about something that is, well, it's completely obvious, and yet at the same time, it is completely impossible. That is the best kind of physics, you see? The kind where the universe looks at your common sense and it just laughs. Now, I want you to imagine you're holding a stopwatch and you decide, because you're feeling adventurous, to race a beam of light from the sun to the earth. So you get in a spaceship. And this is a very special spaceship, fellas, because it can go at 99% of the speed of light. We are going to race a photon, a little packet of light. You look at the sun. It's 93 million miles away. That is a terrible distance. It's so far that even light, which is the fastest thing there is, takes about 8 minutes and 20 seconds to cross it. So the photon leaves the sun. Click, you start your stopwatch, you fly alongside it, you're watching it. And finally, smack, the photon hits the atmosphere of the earth. You stop the watch. If you are standing on earth waiting for that light, your watch says 8 minutes. We know this. We measure it. When you look at the sunset, you aren't seeing the sun now. You're seeing the ghost of the sun from 8 minutes ago. And here is the thing that drives us crazy. If you are the light beam, if you could shrink yourself down and become the photon, do you know how long the trip takes? It doesn't take 8 minutes. It doesn't take 8 seconds. It takes 0. None. To a photon, the moment it is born, in the nuclear furnace of the sun, and the moment it dies, hitting your retina, are the exact same instant. There is no time in between. There is no traveling. To us, the photon is a traveler. It crosses the void of space. It passes Mercury. It passes Venus. It waves hello to the moon. It takes time to do this work. But to the photon, Mercury, Venus, Earth, they are all touching the sun. So here's the mystery we are going to explore today. How can a universe that is 93 million miles wide to us be absolutely 0 inches wide to a particle of light? How can something exist? How can it move? How can it possess energy if it doesn't experience the one thing that defines existence for the rest of us? Time? Nature is playing a trick on us, fellas, a very high-class trick, and we're going to find out how she does it. Now, before we get into the machinery of this, and there is machinery, geometric machinery, we have to understand what it means to experience time. We usually think time is like a river, right? Newton thought this. He thought time was a master clock in the sky. Tick-tock, tick-tock. The clock ticks the same for me, for you, for the man on the moon, and for the light beam. It's a background, a stage. But then Einstein came along, and Maxwell before him, really, and they found out something terrible. They found out the stage is made of rubber. You see, we are used to adding speeds. If I am on a train going 60 miles an hour, and I throw a baseball forward at 40 miles an hour, to the guy on the ground, the ball is going 100 miles an hour. 60 plus 40. Simple arithmetic. My grandmother could do it. So you'd think if I shine a flashlight from a moving car, the light should go faster, right? The speed of the car plus the speed of light. But we measure it. We build delicate instruments, interferometers, mirrors, lasers. We measure it every which way we can. And the answer is always the same. The speed of light is c. Whatever speed you are going, the light is going c faster than you. If you run towards the light, it hits you at c. If you run away from the light at 99% of the speed of light, it still passes you at exactly c. Now stop and think about that. Don't just write it down. Think about how absurd that is. How can you run away from something, but it doesn't get any slower relative to you? Imagine you are running away from a bus, and if you run fast enough, the bus creeps up on you slowly. But light isn't a bus. Light is something else. The only mathematical way that the speed of light can stay the same no matter how fast you move is if your ruler is changing length and your clock is changing its ticking speed. That's the price you pay to keep light constant. You have to break space and time. Now, let's go back to our photon. We know from relativity that the faster you move through space, the slower you move through time. You've heard of the twins, right? One goes to the stars, one stays home. The traveler comes back young. The stay-at-home brother is an old man. Moving clocks run slow. That is a fact. We have put atomic clocks on airplanes and flown them around the world. They come back behind, not broken, just behind. They experience less time. So let's play a game. Let's push it to the limit. If I go 50% the speed of light, my clock slows down a little bit. If I go 99%, my clock slows down a lot. A year for you is maybe a week for me. If I go 99.99999%, a million years for you is a heartbeat for me. But the photon doesn't go 99%. It goes at the speed of light. And at that limit, if you look at the equations, the passage of time stops completely. The clock doesn't just tick slowly, it stops. The hands are frozen. This means that for light, the concept of waiting does not exist. The concept of duration does not exist. Before and after are squeezed together into a single point. Imagine being a photon created in the Big Bang. That was 13.8 billion years ago, according to us. If we look at the cosmic background radiation, we see that light. It has been traveling for billions of years. Empires have risen and fallen. Dinosaurs lived and died. Stars were born and exploded. We feel the weight of those eons. But to that photon, it was born in the Big Bang, and boom, it hit your telescope. Right now, to the photon, the Big Bang is happening now. The end of the universe is happening now. It sees the history of the universe not as a movie, but as a snapshot, one single frozen picture. But wait a minute. I can hear you asking, and you should be asking, Professor, if the photon experiences zero time, how does it get anywhere? Because speed is distance divided by time, distance over time. If time is zero, how can you have speed? If I have to go to the grocery store and I get there in 0 seconds, that means I didn't travel, right? I was already there. So does light just teleport? No. And this is where the second half of the trick comes in. It's not just that time stops, it's that space disappeared. We talked about length contraction. When you move fast, the world squashes in the direction you are moving. Like an accordion being pushed together. If you go fast enough, the distance from New York to London shrinks to a few miles. But if you go at sea, if you go at the speed of light, the length contraction is 100%. The distance becomes zero. So look at the universe from the point of view of the light beam. We see a vast emptiness between the sun and the earth. 93 million miles of cold vacuum. The light beam sees nothing. The surface of the sun and the surface of the earth are touching. They are adjacent points. The photon doesn't have to travel anywhere. It just hops. From the electron in the sun directly to the electron in your eye, whatever gap we see to the light, that gap has been contracted out of existence. This implies something very strange about our reality. It implies that distance and time are not absolute things. They are not the stage of the universe. They are perspectives. They are shadows. We, because we are heavy, clumsy creatures made of matter, we are stuck crawling through time. We are stuck measuring inches and miles. But light connects everything in the universe instantly. This suggests that perhaps, in some four-dimensional geometric sense, everything that has ever happened and everything that ever will happen is all connected by these threads of light forming a rigid block. A block where past and future are just the illusions of our perspective. But why? Why do we have to wait? And light gets a free pass. Why can't we move at the speed of light and escape time? Is it just a rule, a speed limit sign posted by the cosmic police? No matter allowed past this point. No, it's deeper than a rule. It has to do with mass. It has to do with how heavy you are. And it turns out the reason you experience time, the reason you get old, is because you're interacting with the universe in a way that light does not. You are swimming through molasses. Light is flying over the top. So, in the next part of this lecture, we are going to look under the hood. We are going to look at the geometry of space-time, the Minkowski diagrams, and we are going to see exactly why having mass forces you to experience time. We are going to see why time is actually just a direction you can't turn away from. But for now, just remember this. The next time you look at a star and you think, wow, that light took 1,000,000 years to get here, correct yourself. It took 1,000,000 years. To the light, I am touching the star. Now, let's look at the geometry. Now, we have to talk about something that seems very simple. We have to talk about running. We have to talk about how we measure how fast things go. Because if you don't understand this, if you don't really feel it in your gut, then the idea of time stopping is just going to sound like science fiction. And I don't like science fiction. I like science facts that are stranger than fiction. Let's start with what we call common sense. Usually in physics, common sense is wrong, but it's a good place to start. Suppose I am standing on a train, a flatbed train car moving through the countryside, and this train is going 60 miles an hour, and I have a baseball. If I stand on the train and I throw the baseball forward, and let's say I have a pretty good arm, so I throw it at 40 miles an hour, how fast is the ball moving? Well, to me, on the train, it's doing 40. Easy. But what about the guy standing in the cow pasture watching the train go by? He sees the train doing 60. He sees me throwing the ball at 40 on top of the 60. So he takes out his pencil and he adds them up. 60 plus 40 is 100. The ball is going 100 miles an hour relative to the cow. This is what we call Galilean relativity. It's intuitively obvious. You add the speeds. If I run towards you, I hit you harder than if I just walk towards you. If I run away from a bullet, the bullet takes longer to catch me. The speeds subtract. The whole world works this way. Sound works this way. If I scream at you from a moving car, the sound wave gets a little push from the car. The Doppler effect, right? So naturally, when physicists started looking at light in the 1800s, that they thought, okay, light must work the same way. But then we ran into a problem, a beautiful problem. There was this Scottish fellow, James Clerk Maxwell, tremendous mind. He wasn't looking at trains, he was looking at electricity and magnetism. He wrote down 4 equations. You've seen them on T-shirts, I'm sure. Maxwell discovered that if you take an electric field and you jiggle it, you shake an electron back and forth, it creates a magnetic field. And that magnetic field jiggles and creates an electric field, and they leapfrog over each other. Zip, 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 they travel out into space. We call that a wave. Now, Maxwell calculated the speed of this wave. He looked at the constants of nature, how easy it is for electric fields to permeate space, epsilon naught, and how easy it is for magnetic fields, mu naught. He did the math, multiplied these numbers, took a square root, and out popped the number. C, 300,000 kilometers per second, roughly. Maxwell looked at this number and said, wait a minute, that's the speed of light. And he realized that light is just a wiggling electromagnetic field, a discovery of the first magnitude. And here is the catastrophe. Nowhere in Maxwell's equations does it say 300,000 kilometers per second relative to the train. And it doesn't say relative to the sun. It doesn't say relative to the ether. It just says the speed is c, period. Now, do you see the trouble? Maxwell is telling us the speed of light is a constant of nature. It's built into the vacuum. But Newton and our common sense say speeds must add up. So let's try the experiment. Let's do the running problem. Imagine I have a flashlight. I turn it on. The beam shoots away from me at c. Now I jump in my super rocket, and I chase that beam of light. I rev the engines. I get up to half the speed of light, 0.5 c. Common sense says if the light is going c and I'm going 0.5 c, then from my window I should see the light beam moving away from me at the difference of c minus 0.5 c. I should see it moving away slowly. So we do the experiment. We measure it. And what do we find? The light beam is zooming away from me at c. Exactly C. I get ein. I push the throttle. I go to 99% of the speed of light. I am right on its tail. I am breathing down the neck of that photon. I look out the window. It should be inching away from me now, just crawling ahead. I measure the speed of the light beam relative to my ship. And what is the answer? See, it is leaving me in the dust at 300,000 kilometers per second. It's as if I wasn't moving at all. This is madness. This is absolutely crazy. Imagine you are running a race. You are running as hard as you can. You are right behind the guy in front. You can touch his shirt, but he is still running away from you as if you were standing still. How can that be? If I am moving fast, the light must look slower to me, but it doesn't. Nature is refusing to let us catch up. Nature is refusing to let us subtract the speed. Now, for a long time, people thought maybe the experiment is wrong, or they thought maybe there is a wind in space, an ether, and we are just moving through it. Michelson and Morley tried to find that wind. They built a beautiful device, a big stone block floating in mercury so it wouldn't jiggle. They rotated it. They measured light going this way and that way. They wanted to see the Earth plowing through the light. Result? Nothing. Zero. The speed was the same in every direction. So we are stuck. We are stuck with a paradox. Fact 1, we are moving. Fact 2, the speed of light is constant relative to everyone, no matter how they move. These two facts contradict each other. You cannot hold both in your head at the same time using common sense. If speed is distance divided by time, S equals d over t, and if the speed edge stays the same, even when I change my motion, then something else has to give. If the answer to the division problem is always the same, but I am changing my state, then the numerator and the denominator must be lying to me. This is the great insight of Einstein. He was the one who had the courage to say, if the equations say the speed of light is constant, let's believe them, and let's see what happens to the rest of physics. Here is the intuition. You are in the rocket, chasing the light beam. You measure the speed of that beam. You use a ruler to measure the distance it travels, and you use a clock to measure the time it takes. Distance divided by time equals c. I am on Earth watching you. I see the light beam. I measure its speed. Distance divided by time equals c. But we agreed I am standing still. You are moving at 99% light speed. We should get different answers, but we get the same answer. The only physical way this is possible, the only way the math allows this, is if your distance and my distance are not the same length, and if your time and my time are not ticking at the same rate. Think about it. To keep the ratio at the c constant, the ruler in your hand must have shrunk, and the clock on your wall must have slowed down. Nature is conspiring. Nature says, oh, you want to chase a photon? Go ahead. But I am going to slow down your clock and shrink your ruler exactly enough so that when you measure the photon, it's still going c. You see, we used to think that space and time were the stage, rigid, unchanging. A meter is a meter. A second is a second, whether you are on Earth, Mars, or a rocket ship. That was the old idea. But the speed of light is the real boss. The speed of light is the fundamental constant of the universe. It's not just the speed of a particle, it's the speed limit of causality, it's the speed of information. It is the rock-solid anchor. And because C is the anchor, space and time are the ropes. And when you move, the ropes have to stretch, the ropes have to twist. Space and time are not rigid, they are squishy. They are malleable. When you start moving fast, really fast, you are literally bending the geometry of reality to preserve the speed of light. So going back to our mystery, why does light not experience time? Well, if you are the one moving at the speed of light, the conspiracy of nature has to go all the way. To keep cease constant relative to everything else, your clock doesn't just slow down. It has to stop. And your ruler doesn't just shrink. It has to vanish. This isn't just magic. We can draw it. We can see it in triangles. And that is what we are going to do next. I want to show you the mechanism. I want to show you the light clock. Because once you see the triangle, once you see the path the light has to take, you will never look at a clock the same way again. But first, are you with me? We cannot add speeds to light. Therefore, rulers must shrink and clocks must slow. That is the law. Now, let's see how much they slow down. All right? We have a problem. We have established two things that do not seem to fit together. First, if you're on a moving train, things should behave normally for you. Second, the speed of light is the same for you on the train as it is for me standing on the ground. Now, I don't want you to just take my word for it. In science, we don't take people's word for it. We check. And since we can't actually build a spaceship that goes at the speed of light right here in the lecture hall, and the dean would get very upset about the insurance, we have to build a thought experiment. We have to build a machine in our mind. I want to build a clock, but not a grandfather clock with a pendulum and not a wristwatch with a spring. Both have friction, they have gears, they get rusty. I want the most perfect, simple clock universe can build. I call it the light clock. Here is the floor. Here is the ceiling. Let's say the distance between them is L. Now I put a mirror on the floor, and I put a mirror on the ceiling, perfectly parallel. And in between them, I trap a single photon, particle of light. It bounces up, tick. It bounces down, tock. Up, tick. Down, tock. That is our clock. One tick-tock is the time it takes for the light to cross the distance L and come back. Now, light travels at speed. So the time for one tick is very simple. Distance divided by speed. Keep that in your pocket. That is the rest time. That is the time measured by the guys sitting next to the clock. Now, things get interesting. We put this light clock on a train. On a very fast train. And you are sitting on the train with the clock. What do you see? Well, you're moving with the clock. The mirrors are right there in front of you. You see the photon go up and come down. Vertical line, up and down. To you, this clock is ticking normally. Tick-tock, no problem. But I'm standing on the platform, the station, and I'm watching you zoom by at a tremendous speed, let's say velocity v. Now, I want you to visualize what I see. When the photon leaves the bottom mirror, the train is here. But by the time the photon hits the top mirror, the train has moved. The ceiling has shifted to the right. So the photon can't just go straight up. If it went straight up, it would miss the mirror. It would hit the wall of the back of the train. But it does hit the mirror. So to me, standing on the ground, the photon doesn't travel vertically. It travels diagonally. It goes up and to the right, slant. Then it hits the top mirror. Then the train keeps moving, so the bottom mirror shifts to the right. The photon comes down diagonally, slant. Look at the geometry, fellow. Look at the path. On the train, the path was a straight vertical line up. From the platform, the path is a hypotenuse of a triangle. And what do we know from high school geometry? The hypotenuse is longer than the vertical side. The diagonal path is longer. There is no debating this. It is a geometric fact. If the train moves, the light must travel a longer distance to bounce between the mirrors. Now, here is the trap. In the old physics, in Newton's physics, we would say, well, clearly, if the light has to go further, it must speed up. Just like if I throw a ball while running, the ball goes faster. If the ball goes faster, it can cover the longer distance in the same amount of time. Tick-tock equals tick-tock. Time is safe. But we can't do that. We already agreed. Nature has signed a contract. The speed of light is constant. The speed of light along that long diagonal line is exactly the same as the speed of light along the short vertical line. It is steep. So let's think. We have a longer distance, we have the same speed. Speed equals distance divided by time. Or let's flip it. Time equals distance divided by speed. If the distance numerator gets bigger, and the speed denominator stays the same, what happens to the time? The time must get bigger. There is no way out of it. The tick seen from the platform takes longer than the tick seen on the train. The seconds are longer. The minutes are fatter. Time itself is stretching out. This isn't a mechanical failure. It's not that the motion shook the clock and broke the spring. We used a light clock. We used the fundamental speed of the universe as our pendulum. If this clock slows down, it means time itself is slowing down. This is what we call time dilation. Now you might say, okay, Feynman, that's a nice picture, but how much? How much does it slow down? We can figure it out. It's just the Pythagorean theorem. A squared plus b squared equals c squared. Look at the triangle I drew. The vertical side, that's the height of the train car. That's the distance the light travels in the rest frame. The horizontal side, that's how far the train moved. The hypotenuse, that's the path of the light beam. If we do the algebra, and I won't bore you with every step, or you can do it for homework, but if you set the speed of light to c and the speed of the train to v, you get a conversion factor, a translation key between your time and my time. We call it gamma, the Lorentz factor. And here's the formula. It's the most famous formula in relativity, perhaps even more useful than E equals mc squared. D prime equals T over the square root of 1 minus DI squared over C squared. Don't let the symbol scare you. Let's read it like a sentence. This is the time on the train, the short time. T prime is the time on the platform. That's the long time. Look at the bottom, the square root, 1 minus V squared over C squared. Let's plug in some numbers to see how nature behaves. Suppose the train is not moving. V equals 0. 0 divided by C squared is 0. 1 minus 0 is 1. The square root of 1 is 1. So T prime equals T. Time is the same. This is our everyday life. This is why you don't notice this effect when you walk to the grocery store. You're too slow. Now, let's get that train moving. Let's go at 80% the speed of light. V equals 0.8 T. 0.8 squared is 0.64. 1 minus 0.64 is 0.36. The square root of 0.36 is 0.6. So T hat prime equals T divided by 0.6. Dividing by 0.6 is the same as multiplying by 1.6. So if 10 minutes pass on the train, 16 minutes pass for me on the ground. You have lived 10 minutes. I have aged 16 minutes. You are effectively traveling into the future simply by moving fast. Now, I want you to notice something about this formula, something very dangerous one. Look at that bottom number again. The square root of 1 minus V squared over C squared. What happens as V gets bigger? As V gets closer to C, the fraction V squared over C squared gets closer to 1. So the term 1 minus something almost 1 gets tiny. It gets closer to 0. We are dividing by a smaller and smaller number. And you know from arithmetic, if you divide by a tiny number, the answer blows up. It gets huge. If you go at 99% the speed of light, 1 year for you is 7 years for me. If you go at 99.99%, 1 year for you is 70 years for me. If you go at 99.99999%, you could watch the pyramids being built and the skyscrapers falling down all in the span of a nice afternoon nap. This is real. This happened. We see particles called muons. They're hitting the earth from space. They have short lives. They should die before they reach the ground. But because they are moving so fast, their internal clocks run slow and they live long enough to hit our detectors. We literally see the ghosts of particles that should be dead, kept alive by the speed of their travel. But now we have to ask the ultimate question, and the question that brings us back to the title of this lecture. We looked at V equals 0. We looked at V equals 0.8 C. We looked at V equals 0.99 C. What happens if we set V equal to C? What happens if you are the photon? Let's look at the math. V equals C. V squared over C squared equals 1. 1 minus 1 equals 0. Square root of 0 is 0. We are dividing by 0. In mathematics, that's a sin. You can't do it. The equation screams at you. But in physics, it tells us something profound. If you divide by 0, the result is infinity. This means the dilation is infinite. This means the stretching of time is absolute. For a photon, a single second stretches out to fill the entire lifespan of the universe, or to put it the other way around. For a photon, the entire history of the universe is compressed into 0 seconds. The photon does not have a clock. It cannot have a clock. Because for a clock to tick, there must be a before and an after. But at the speed of light, before and after are piled on top of each other. You see, the geometry forces us to this conclusion. It's not just that light moves fast. It's that light exists on the very edge of reality, the boundary, where time ceases to have any meaning at all. But if time stops, surely space must do something equally strange. Because we know space and time are linked. If I have infinite time, do I have infinite space? Actually, it's the exact opposite. And that is what we need to talk about next, the pancake universe. Now, we have to look at the edge of the cliff. We have been talking about trains. We have been talking about rockets. We have been playing it safe, dealing with speeds like 50% of light, or 80%, or even 99%. And we saw that as you go faster, your personal clock, the beating of your heart, the ticking of your watch, the vibration of your atoms, it all slows down relative to the rest of the universe. If you go to the center of the galaxy, Sagittarius A star, that big black hole sitting there, that is roughly 26,000 light years away. If you go at normal speeds, you will die of old age before you get out of the solar system. But if you go at 99.99999% of the speed of light, you could make that trip in what feels like a few weeks. You eat a few sandwiches, read a book, and you are there. But when you arrive, 26,000 years have passed on Earth. Everyone you knew is gone. Empires have risen and fallen. You have traveled into the future. This is all very interesting. It is the stuff of science fiction story, but it is not what light does. Light does not go 99%. Light does not go 99.99999%. Light goes at C. So we have to be brave. We have to take this formula, the Lorentz factor, and we have to plug in the number that breaks it. Let's look at the bottom of the fraction again. The square root of 1 minus v squared over c squared. Now let v equal c. Let the velocity be the speed of light. What is c squared divided by squared? It is 1. So the term inside the square root becomes 1 minus 1 equals 0. And the square root of 0 is 0. So now let's look at the time equation full. T prime equals t over 0. We are dividing by 0. Now in your calculus classes, the mathematicians, and they are very precise people, bless their hearts, they will tell you that dividing by 0 is undefined, and they will tell you it is a singularity. They might even slap your hand if you try to do it. But in physics, the math is talking to us. The math is screaming at us. When an equation blows up, when the denominator hits 0 and the answer shoots off to infinity, nature is telling us that we have hit a wall, a fundamental limit of reality. What does it mean if the time dilation factor is infinity? It means that the stretching of time is infinite. It means that a single second for the photon is stretched out to cover eternity for us. Or to flip it around to the photon perspective, any amount of time for us, 1,000,000 years, 1,000,000,000 years, is compressed into 0 seconds for the photon. Think about what this implies. I want you to really try to inhabit the mind of a photon. I know it has no brain, it has no mass, but use your imagination. Imagine you are a photon created in the very early universe. Let's say from the hot plasma right after the Big Bang. This is the cosmic microwave background radiation we talk about. That light has been traveling for 13.8 billion years. It has crossed the expanding void of the cosmos. It has watched galaxies form from dust. It has watched stars ignite and explode. It has watched the earth cool from a ball of magma. It has watched life crawl out of the ocean. And finally, tonight, it hits the dish of a radio telescope in New Jersey. To us, that photon is an ancient messenger. It is the oldest thing we can see. We look at it with reverence. Look at this, we say. This light is 13 billion years old. But to the photon, it was born. And immediately, instantly, without a single tick of a clock, it hit the telescope. The birth in the Big Bang and the death in the telescope happened at the exact same moment. There was no during. There was no travel. There was no waiting. The photon did not experience 13 billion years. It didn't experience 13 seconds. For the photon, the universe is not a place where things happen in a sequence. It is a place where the beginning and the end are connected. This is a very disturbing idea. We are biological creatures. We are built on clocks. Our hearts beat, thump, thump, 1 second. Our neurons fire, milliseconds. Our cells divide, days. We are trapped in the flow of time. We are like leaves floating down a river. We can't stop. We can't go back. We just float downstream and getting older. But light is not in the river. Light is the bank. Light exists outside the flow. If you could be a photon, you would not know what age is. A photon cannot get old. Have you ever wondered why light doesn't decay? A proton might decay. We don't know yet. Atoms decay. Even black holes will eventually evaporate. But a photon from the beginning of time is just as fresh, just as energetic, just as new as a photon created by this light bulb 1 nanosecond ago. Why? Because it hasn't had time to wait. Because for the photon, zero time has passed. So we have this picture of the universe. Point A, the sun. Point B, your eye. We draw a line. We say the light travels from A to B, and we assign a time to it. T equals 8 minutes. But the math tells us that for the thing doing the traveling, the distance is zero, length contraction, and the time is zero with time dilation. So is it really traveling? Or is it doing something else? Maybe. And this is where we get into the deep structure of quantum mechanics. Maybe light isn't a thing that moves. Maybe light is an interaction. Maybe the universe is just a web of connections. When an electron on the sun jiggles and an electron in your eye jiggles, they are exchanging a photon. But if the time is zero and the distance is zero, then those two electrons are, in a very real sense, touching. They are touching across the vacuum. The photon is just the name we give to that handshake, the handshake that happens across 93 million miles. Now, I want to address a question that always comes up. Professor, if light doesn't experience time, how does it have a frequency? How does it wave? Because a frequency is cycles per second. Red light waves 400 trillion times a second. If a second doesn't exist for light, how can it wave? This is a beautiful confusion. The frequency belongs to us. The waving happens in our time. We are the ones watching the electromagnetic field oscillate. We are the ones with the clocks measuring the beats. To the photon, it is just a frozen state of existence. It carries energy. It carries momentum. It carries information. But it carries them as a static geometric object. It is we, the observers with mass, who chop that object up into seconds and cycles. We are the ones slicing the salami. The photon is the whole salami. So we have crashed into the wall. We have found that V equals C is a singularity. It is a place where the rules of before and after collapse. And this leads us to the most uncomfortable realization of all. If the universe is filled with light, if every atom in your body is held together by the electromagnetic force, which is mediated by photons, if the gravity holding you to the floor is mediated by fields that travel at the speed of light, then deep down, underneath the heavy, slow world of matter, the universe is a place where time does not exist. Time is an emergent property. Time is something that happens to heavy things. Time is the penalty for being stuck in one place. If you could shed your mass, if you could turn all your atoms into light, you would instantly become eternal. You would be everywhere on your path at once. The moment of your transformation and the moment of the end of the universe would be the same moment. But you can't, because you have mass. You are heavy. You are sticky. And that brings us to the next mystery. Why? Why do we have mass? Why can't we go at sea? What is holding us back? Why does the universe forbid us from joining the timeless dance of the light? It turns out there is a reason. There is a field, a thick invisible soup, that permeates the entire universe, and we are wading through it. And that wading is what creates the illusion of time. Let's talk about the Higgs field. Let's talk about the origin of mass. The difference. So why can't we do this? Why are we stuck in the slow lane, forced to get old and pay taxes? Mass. We have mass. Matter is sticky. In modern physics, and this is something we're just really getting a handle on, we think of mass as a drag. You are swimming through a field, the Higgs field. You're bumping into it. That bumping slows you down. Because you are slow, less than c, you experience the passage of time. Light has no mass. It doesn't interact with that field. It slips through the net perfectly. Because it has no mass, it must move at c. And because it moves at c, it cannot experience time. Time is the tax you pay for having mass. So wouldn't it be nice? Wouldn't it be wonderful to be a photon? To zip from one end of the galaxy to the other in an instant? To never wait in line at the post office? To never get gray hair? To never have your knees creak when it rains? Eternal youth. Instantaneous travel. The ultimate freedom. But we can't do it. We are stuck. We are plodding along, watching the clock tick, feeling the weight of the years. And we have to ask ourselves, why? What is the difference between me, a collection of atoms, and that beam of light? Why does the light get a free pass and I have to pay the toll? The answer lies in one simple, heavy word: mass. We have mass. Matter is sticky. Now, what is mass? For a long time, since Newton, really, we thought mass was just a property of stuff. You know, how much oomph it had. If I kick a bowling ball, it hurts my foot more than if I kick a beach ball. The bowling ball has more mass. It resists me. It has inertia. But why? Why does the universe care if I kick a bowling ball? Why does it push back? In modern physics, and this is something we have really only pinned down in the last few decades with the Higgs mechanism, we have a different picture, a much more beautiful picture. We don't think of mass as just a number painted on a particle. We think of mass as an interaction. Imagine the universe isn't empty. Imagine that all of space, every inch of this room, with the space between the stars, the space inside your atoms is filled with a fluid, a field. Let's call it the Higgs field. But it's not like water. It's more like molasses or thick syrup. It is everywhere. You can't pump it out. It is the background of reality. Now imagine a particle trying to move through this syrup. If you are an electron or a quark, the things inside your protons, you interact with this field. You are popular with the field. As you try to move, the field clusters around you. It clings to you. It drags on you. It says, hey, not so fast. Stay here for a while. That drag, that resistance is what we call mass. You feel heavy because you're swimming through this invisible ocean. You are bumping into the Higgs field constantly. This piece of chalk feels solid. But really, it is a collection of particles that are struggling to move through the Higgs field. That struggle is what gives it weight. And because you are struggling, because you are dragging this anchor behind you, you cannot reach the speed limit. You push and push, you pour energy in, but the drag gets harder. The field resists you more. You can get close to C, you can get to 99.9%, but you can never quite shake off the syrup. You can never reach the speed of light. And because you are moving slower than C, your clock starts ticking. Because you are not at the limit, time dilation is not infinite. time flows for you. Moments pass. Cells divide. You age. But the photon is different. The photon is a ghost. The photon travels through the Higgs field, but it does not interact with it. It is invisible to the syrup. It cuts right through. No drag, no friction, no clustering. It doesn't even know the field is there. And here is the rule of the universe, a very strict rule. If you have no mass, you must move at c. You don't have a choice. You can't slow down. You can't take a break. If you don't interact with the field, the geometry of space-time spitballs you out at the maximum possible velocity. A photon is born moving at the speed of light. It lives its whole life at the speed of light. And it dies hitting something at the speed of light. It never accelerates, it never decelerates, it just is. And because it moves at c, it escapes time. So do you see the tragedy of our existence? Well, we experience time because we are heavy. Time is the tax you pay for having mass. Time is the penalty for interacting with the universe. If you could magically turn off your interaction with the Higgs field, if you could switch off your mass, you would instantly disintegrate and fly apart at the speed of light. Your watch would stop. You would become timeless. But you would also cease to be you. You would just be a spray of radiation. So we are stuck with a compromise. To exist as matter, to exist as complex beings who can think and love and attend physics lectures, we have to be heavy. We have to be slow. And the price of that existence is that we have to endure the passage of time. Now, some of you sharp students might be thinking, Professor, you said most of the mass comes from the Higgs field, but protons are made of quarks and quarks are light. Where does the rest of the mass come from? You are right. That's a detail, but a good one. Most of your mass actually comes from the energy of the gluons holding your quarks together. E equals mc squared. The energy acts like mass. But the principle is the same. Energy or interaction creates inertia. Inertia prevents you from going at c. And anything that goes slower than c must experience time. So we have two worlds. We have the world of light, timeless, spaceless, a two-dimensional sheet of instant connection. And we have the world of matter, heavy, slow, trapped in the river of time, watching the scenery go by. We live in the slow lane, but because we are in the slow lane, we get to have a history. We get to have a past and a future. Light doesn't have a past, light doesn't have a future. It only has an eternal now. I don't know about you, but I kind of like having a past. I like having memories. So paying the tax of time isn't so bad, considering the alternative is being a flash of light that hits a wall and vanishes. But this brings us to the final thought, the big picture. If light connects the universe instantly, and if we are just lumps of matter floating in this web of light, right, what does the universe really look like? If we could step outside of our slow, heavy perspective, what would we see? We would see a structure, a geometric object, a block. And that is where I want to leave you today, with the idea of the block universe. Let me draw you one last diagram. So where does this leave us? We started this morning with a stopwatch. We tried to race a beam of light, and we found out that the universe is not what it seems. We found out that if you move fast enough, space shrinks to nothing. We found out that if you're a photon, time shrinks to nothing. We found out that the only reason we are sitting here, getting older, worrying about the future, is because we are heavy. We are stuck in the mud of the Higgs field. But if you take all these things we've written on the board and you try to put them together into one picture, what does that picture look like? We usually think of the world as happening right now. Tick-tock, tick-tock. The past is gone. It's a memory. The future hasn't happened yet. It's a dream. And the now is this razor-thin slice of reality that keeps moving forward. That's how it feels to be a biological machine. But physics tells us a different story. If light connects the sun in your eye instantly, if the distance between them is zero for the thing that connects them. And if, as we learned in relativity, my now can be your past if I am moving fast enough relative to you, then the distinction between past, present, and future is not a rigid law. It is an illusion, a stubbornly persistent illusion, as Einstein called it. This suggests that the universe isn't happening. It suggests the universe just is. Imagine a loaf of bread. In a long rectangular loaf, you can slice it straight down. That's one way to look at time. I can slice it at an angle. That's another observer's time. The loaf is the same. The crumbs are the same, but the slices of now are different. This implies that the universe is a giant geometric object, a four-dimensional block. We call it the space-time block. And inside this block, every event that has ever happened and every event that will ever happen is already there. Your birth, it's a point in the block. Coordinate X, Y, Z, T. This lecture, another point. Your death, another point. The end of the solar system, another point. And your life, your entire existence is just a line connecting those points. We call it a world line. You think you are moving along the line. You think you are living it moment by moment. But from the perspective of the geometry, the line is just drawn there, indelible, static, frozen. And the light beam is just a thread connecting 2 points on that map. It doesn't move along the thread. The thread is just the structure of the block itself. It is the stitching that holds the loaf of bread together. To the photon, the block is squashed flat. The beginning and the end are touching. It sees the whole picture at once. Now, this is a very beautiful idea. It's elegant. It solves all the math problems. But here is the thing that keeps me up at night. Here is the question that I want you to take home with you because I don't have the answer. If light doesn't experience time, and if almost all the fundamental interactions in the universe are exchanged by particles moving at the speed of light, think about it. Your atoms are held together by electromagnetism, photons, moving at c, timeless. The nucleus of your atoms is held together by gluons, moving at c, timeless. Gravity, we think it's mediated by gravitons, moving at c, timeless. So the glue that holds reality together, the machinery that makes the universe work, operates in a realm where time does not exist. The basement of the universe is timeless. So where does time come from? If the fundamental parts of you are timeless, why do you feel time? Is time actually real? Does it exist at the bottom level of physics? Or is time just a macroscopic mistake? Is it a blurry vision? Maybe time is just what happens when you have so many trillions of atoms interacting that you lose track of the details. Maybe the past is just our inability to count the variables. Maybe if we could see the universe as it really is, if we could see it with the eyes of a photon, we would see the whole glorious four-dimensional sculpture, complete, perfect, and finished all at once. We are too clumsy to see it. We are too heavy. So we are forced to read the book page by page, word by word, wondering what happens next. But the photon knows the whole story, because for the photon, the book is already written. So think about that tonight. Go outside. It's a clear night in Pasadena. Look up at the stars. You'll see light that left a star 1,000 years ago. And you will think, I am looking into the past. But correct yourself. Remember the geometry. To that light, there was no journey. To that light, there is no path. That light is a bridge, a zero-length bridge that connects the nuclear fire of a distant sun directly to the electrochemical firing of your brain. You aren't just looking at the universe. In a very real geometric sense, you are touching it. Thank you. Today's question is how the speed of light was first measured. Now, I want you to stop and think about the absolute absurdity of this problem. Look around the room you're sitting in right now. You flip a switch and instantly the room is flooded with light. You look out the window at a tree a mile away and you see the tree exactly as it is the very instant you look at it. For thousands of years, the smartest people on the planet, guys like Aristotle, Descartes, the big name, looked at this exact same phenomenon and concluded that light does not travel at all. They said, look, there is no delay. Light isn't a thing that moves from point A to point B. Light is simply a property of the universe. It is a rigid connection. They thought of it like a stick. If I have a stick that is 1,000,000 miles long and I push my end, your end moves at the exact same time, instantaneous. No speed. But in physics, we don't just accept what our eyes casually tell us. We have to be suspicious. We have to ask if light is not instantaneous, even if it actually takes time to go from the lamp to your eyeball, how would you even know? To measure the speed of anything, you need exactly two things. You need a ruler to measure the distance, and you need a clock to measure the time. You watch a horse run down a track. You know the track is 1 mile long. You start your stopwatch when the horse starts. You stop it when the horse finishes. You divide the distance by the time, and bang, you have the speed. You can do this for a train. You can do it for a sound wave. You see a lightning strike. You wait, you hear the thunder. 3 seconds later, you know sound takes time. But light is the thing you are using to see the horse, the train, and the lightning. You never see the lightning before the lightning illuminates the clouds. So if light actually has a speed, it must be moving so incredibly fast that no ordinary physical clock you can build with gears and springs can tick fast enough to catch it, and no ordinary distance on Earth is long enough to make a measurable difference. The time interval between light leaves a lamp and light hits your eye is so close to zero that you can't measure it, and you cannot divide by zero. So we are stuck. How do you measure something that outruns your ability to measure it? You have to cheat. You have to either find a way to stretch the distance to an astronomical, mind-boggling scale, or you have to invent a clock that ticks not in seconds, not in tenths of a second, but in millions of a second. This lecture is the exact step-by-step mechanical story of how human beings figured out how to do exactly that. No magic, no abstract philosophy, no sugarcoating. Just pure brute force mechanics, gears, mirrors, the moons of Jupiter, and simple unbreakable geometry. I'm going to walk you through how we trapped light, exactly how the instruments were built, what went wrong, and how we got the numbers. Let us start at the beginning. The year is 1638, Galileo Galilei. He is the first guy to say, let's stop arguing philosophy and actually do an experiment. He realizes you need a controlled setup. He proposes something very simple, very logical. You take two guys, let's call them man A and man B. You give each of them a lantern, but not a regular lantern, a lantern with a mechanical wooden shutter over it so you can block the light and then suddenly reveal it. You take these two guys and you put them on two different hilltops near Florence, Italy. Let's say the hills are 1 mile apart. It is dead of night, pitch black. Here is the plan. Man A opens his shutter. The instant the light escapes, it travels 1 mile across the valley to man B. Man B is staring into the dark, the very microsecond. Man B sees the light from man A. He rips open his own shutter. The light from man B travels 1 mile back to man A. Man A has a water clock, a device that drips water at a steady rate into a measuring cup. He starts the clock when he opens the shutter. He stops the clock when he sees the return light. You have the distance, 2 miles total round trip. You have the time, the amount of water in the cup. Divide distance by time, you get the speed of light. Galileo actually tried this. He sent his assistants out to the hills. What happened? Man A opened his shutter, and absolutely instantly, he saw the light from man B. There was a delay, but it was just the physical clumsiness of the guys moving their hands. So Galileo says, okay, the distance is too short. They move the hills further apart, 2 miles apart, 3 miles apart. They do it again. The result is exactly the same. The delay did not increase. Why did this fail? We have to analyze the physical mechanics of the human body. What is actually happening on that hill? Three distinct events are taking place. Event 1, light travels from hill A to hill B. Event 2, the light enters man B's eyeball. It hits his retina. A chemical reaction happens. An electrical signal travels up his optic nerve to his brain. His brain processes the signal. Aha, I see light. His brain sends a new electrical signal down his spinal cord, out to his arm, into his hand muscles. His muscles contract and he pulls the wooden shutter open. Event 3, light travels from hill B back to hill A. Today we know that human biological reaction time, event number 2, takes about 0.2 seconds if you're really paying attention. Do you know how far light can travel in 0.2 seconds? It can travel around the entire equator of the Earth 1.5 times. The actual time it took for the light to cross the 1 mile valley between the two hills was about 0.000005 seconds. Galileo was not measuring the speed of light. He was measuring the speed of his assistant nervous system. The biological noise completely swallowed the physics signal. Galileo looked at his water clock, looked at the data, and concluded exactly what a good scientist should conclude. He wrote, "If the speed of light is not infinite, it is at least extraordinarily swift." He proved that earthly distances are simply too pathetic, too short to catch light with a human hand. This leaves us with a tremendous cliffhanger. If the Earth is too small and our hands are too slow, where do we go? We have to leave the Earth. We have to go to space. We move forward in time to the year 1676. A Danish astronomer named Ole Rømer is working at the Royal Observatory in Paris. Now, Rømer is not trying to measure the speed of light. Nobody is paying him to do that. He is trying to solve the biggest, most expensive practical problem of the 17th century: navigation at sea. If you're on a ship in the middle of the ocean, finding your latitude, how far north or south you are, is easy. You just measure the angle of the North Star above the horizon. But finding your longitude, how far east or west you are, is a nightmare because the Earth is spinning. To know your longitude, you need to know exactly what time it is back at your home port, say Paris. If you know it is exactly 12 o'clock noon in Paris, but the sun is directly over your head on the ship, meaning it is local noon. You compare the times, calculate the rotation of the Earth, and you know exactly where you are. But there is a catch. You need a clock to keep Paris time on the ship. In 1676, the only accurate clock's a pendulum clock. Put a pendulum clock on a wooden ship rocking in the Atlantic Ocean, and it becomes completely useless. So astronomers say, don't use a mechanical clock, use the sky. The sky is a giant, perfect clock mechanism made by gravity. They look at Jupiter. Jupiter is huge, and it has moons. The innermost moon of Jupiter is named Io. Io orbits Jupiter incredibly fast. It goes around Jupiter once every 42.5 hours. It is a highly predictable, unbreakable mechanical system, and because Jupiter casts a massive shadow into space every time Io goes around the back of Jupiter, it hits that shadow and completely disappears. An eclipse, then a few hours later it pops out the other side. The idea was brilliant. Rømer's boss tells him, watch Io, time exactly when it goes into the shadow and exactly when it comes out. Do this for years, build a table, a massive schedule of exactly when every eclipse will happen for the next 10 years in Paris time. Then we print a book. We give it to a ship captain. The captain is in the middle of the ocean. He points his telescope at Jupiter. He waits for Io to disappear. He looks at his book. The book says Io will disappear at exactly 10:14 p.m. Paris time. Boom. The captain now knows it is 10:14 p.m. in Paris. He checks his local time, calculates his longitude, and he doesn't crash into a reef. So Rømer goes to work. He sits at his telescope night after night, freezing in the Paris observatory, logging the exact minute and second Io vanishes. But after a few years of data, Rømer looks at his logbook and he notices something deeply disturbing. The celestial clock is broken. The eclipses are not happening on schedule. Let's look at the geometry of the solar system. You have the sun in the middle. Earth is orbiting relatively close to the sun. Jupiter is way out there, orbiting much slower. When Earth and Jupiter are on the exact same side of the Sun, meaning Earth is as close to Jupiter as it ever gets, Romeo logs the eclipses. They happen exactly 42.5 hours apart. Perfect. But as the months go by, the Earth moves faster in its orbit. Earth starts swinging around the Sun, physically moving away from Jupiter. As Earth moves further away, Roma notices that the eclipses of Io start happening late. They are a few seconds late. Then, a week later, they are a minute late. 6 months pass. Earth is now on the exact opposite side of the Sun from Jupiter. Earth is now at its absolute maximum possible distance from Jupiter. The distance has increased by exactly the diameter of Earth's orbit. Romer checks the eclipse. It is late. It is a full 22 minutes behind the schedule he calculated. Then, Earth continues its orbit. It starts coming around the other side of the Sun, physically moving back toward Jupiter. What happens to the eclipses? They start catching up. They are 15 minutes late, then 10 minutes late, then 5. Another 6 months pass. Earth is back on the same side of the Sun, right next to Jupiter again. Romer checks the eclipse. Boom! It is exactly back on schedule, not 1 second late. Now, Romer has to think like a physicist. What is happening? Is Io physically slowing down and speeding up in its orbit? Impossible. Io is a massive rock floating in a frictionless vacuum. Conservation of angular momentum says it cannot change its speed. The physical event, the moon entering the shadow, is happening at perfectly regular intervals. The discrepancy is not in the event. The discrepancy is in the signal carrying the information of the event to Earth. Romer realizes the monumental truth. When Earth is far away, the light reflecting off Io, the visual information that the eclipse has happened, has to travel an extra distance. It has to cross the entire diameter of the Earth's orbit around the Sun. The eclipse is 22 minutes late because it literally takes light 22 minutes to cross that massive expanse of empty space. Romer had done it. He found the astronomical distance and he used the Earth's orbit as the clock. Now let's do the arithmetic, because physics is numbers. In 1676, astronomers had a rough estimate of the diameter of Earth's orbit. They thought it was about 276 million kilometers. Romer has the distance, 276 million kilometers. Romer has the time, 22 minutes. Let's convert that to seconds. 22 times 60 is 1,000 is 320 seconds. Speed equals distance divided by time. 276 million divided by 1,320. Romer calculates the speed of light to be roughly 210,000 kilometers per second. Now, let's be totally honest here. The actual, true speed of light, as we know it today, is 299,792 kilometers per second. Romer's number was off by about 25 to 30%. Why? Did his logic fail? No. His logic was flawless. The error was in the input data. First, the astronomers in the 17th century didn't have radar. Their measurement of the distance from the Earth to the Sun was slightly too small. Second, Romer's timing of exactly when Io completely vanished was a bit fuzzy because the Earth's atmosphere boils and distorts telescope images, and Io fades out gradually. It doesn't just instantly click off. We know today that light actually takes about 16.6 minutes to cross Earth's orbit, not 22 minutes. But Romer's exact number does not matter one bit. What matters is the monumental shift in human understanding. He proved with hard, indisputable observational data that light is not instantaneous. Light is a physical thing moving at a finite speed through the vacuum of space. You would think the scientific community threw him a parade. They didn't. Scientists are ruthless skeptics. Many prominent scientists, including the director of his own observatory in Paris, a guy named Cassini, completely rejected Romer's paper. Cassini said, Jupiter's atmosphere is probably causing the delay. Or maybe orbits aren't perfectly circular. There are too many variables in planetary motion to prove something as fundamental as the speed of light. They demanded more. They said, if light takes time to travel, show us another way. Show us independent verification using a completely different physical mechanism. All right, 50 years go by. It is now 1728. An English astronomer named James Bradley is going to accidentally prove Roma right while trying to measure something entirely different. Bradley is obsessed with finding stellar parallax. Let me explain parallax because it is crucial. Hold your thumb up right in front of your nose, close your left eye, and look at your thumb with your right eye. Notice what part of the background wall your thumb is blocking. Now, don't move your thumb. Close your right eye and open your left eye. Your thumb appears to jump horizontally against the wall. Did the thumb move? No. Your point of observation moved. The distance between your two eyes creates a baseline, and changing the observation point shifts the apparent position of the foreground object relative to the background. Bradley wants to scale this up to the size of the solar system. If the Earth is orbiting the Sun, then in January, the Earth is on one side of the solar system. In July, it is on the exact opposite side. That is a baseline of 300 million kilometers. And then if you take a telescope and point it at a relatively nearby star in January, and then look at the exact same star in July, that nearby star should appear to shift its position slightly against the super-distant background galaxies. If you can measure that tiny angular shift, you can use high school trigonometry to calculate exactly how far away the star is. So Bradley buys a massive, highly precise telescope, but a telescope on a wooden tripod will warp and shift with the weather. So he takes the telescope tube and literally bolts it to the brick chimney of a house so it absolutely cannot move. He points it straight up at the zenith, aiming at a specific star called Gamma Draconis. For an entire year, Bradley carefully measures the exact position of Gamma Draconis in the eyepiece, and he finds a shift. The star is moving. Over the course of a year, the star traces a tiny, perfect little ellipse in the sky. Bradley is thrilled. He thinks he has found parallax, but then he looks closer at the data. He looks at the timing of the shift and his heart sinks. The mechanics are entirely wrong. Think about the geometry. If this shift was caused by parallax, the star should be at its maximum extreme left position when the Earth is at its maximum extreme right position in the orbit. The maximum shift should happen at the exact ends of the baseline. But Bradley's star was not doing that. The star was showing its maximum shift when the Earth was exactly in the middle of the baseline, moving parallel to the star at its absolute maximum velocity. This is not parallax. This is something completely different. Bradley is stumped. He walks up and down the River Thames trying to figure out what is wrong with his telescope. The story goes that he is on a sailboat on the river. He looks up at the wind vane on top of the mast. He notices that when the boat turns and speeds up, the wind vane changes direction. The wind itself didn't change direction. The apparent wind changed because of the motion of the boat. Boom. Bradley has an epiphany. He invents the umbrella and the rainstorm analogy. I want you to picture this exactly. Imagine you are standing completely still in a rainstorm. There is no wind. The rain is falling perfectly straight down from the sky. You are holding a tall, narrow pipe straight up in the air. The raindrops fall straight down through the pipe without hitting the side. Now, I want you to start running forward as fast as you can, still holding the pipe straight up. What happens? Even though the rain is falling straight down because you are physically moving forward, the side of the pipe is going to slam into the raindrop before the drop can make it out the bottom. From your perspective, running, the rain feels like it is slanting into your face. If you want the rain to fall clean through the pipe while you're running, what do you have to do? You have to tilt the pipe forward into the direction you are running. Bradley realized his telescope was the pipe. The starlight from Gamma Draconis was the rain, and the Earth was him running. The light from the star is falling perfectly straight down onto the Earth. But the Earth is moving through space in its orbit around the sun at a massive velocity, about 30 kilometers every single second. In the tiny fraction of a second that it takes the light to travel from the top lens of the telescope down the tube to the eyepiece at the bottom of the telescope is physically carried sideways by the Earth's motion. If the telescope is pointed straight up, the light entering the top will hit the inside wall of the brass tube before it reaches Bradley's eye. To make the starlight hit the exact center of the eyepiece, Bradley had to tilt the telescope slightly forward into the direction of Earth's motion. As the Earth goes around the sun, the direction of its forward motion changes 360 degrees over the year. So the direction you have to tilt the telescope changes 360 degrees over the year, causing the star to trace a tiny circle or ellipse in the sky. This effect is called stellar aberration. Now, why is this so beautiful? Because it is pure, absolute vector addition. It is a simple right triangle. The vertical side of the triangle is the speed of the falling rain, the speed of light. The horizontal side of the triangle is the speed of the runner, the speed of the Earth in its orbit. The angle of the hypotenuse is the exact angle that Bradley had to tilt his telescope. Bradley measured that angle. It was incredibly tiny, 20.5 arc seconds. To give you an idea of how small that is, 1 degree is a tiny sliver of the sky. An arc minute is 1/60th of a degree. An arc second is 1/60th of an arc minute. 20.5 arc seconds is the size of a quarter seen from 3 football fields away. But Bradley measured it. Now look at the triangle. If you know the horizontal speed, Earth's orbit, which we knew fairly well, and you know the angle, 20.5 arc seconds, trigonometry dictates that there is only one mathematically possible length for the vertical side. Bradley crunched the numbers. Earth speed divided by the tangent of 20.5 arc seconds. His result, the speed of light, is 295,000 kilometers per second. This is astonishing. Look at what Bradley did. He didn't use Jupiter's moons. He didn't use a stopwatch. He used the geometry of a moving tube to calculate that light takes 8 minutes and 12 seconds to reach Earth from the sun. His number was within 1.5% of the true modern value. He completely validated Roma. Light is not instantaneous, and the debate is over. But physicists are greedy. We are never satisfied. Yes, we had a number, but look at how we got it. We had to use the entire solar system. We had to rely on the orbit of the Earth, the distance to the sun, celestial mechanics. We wanted absolute control. We wanted to take light, trap it in a room, and measure it with earthly rulers and earthly clocks, but we still have Galileo's problem. Over earthly distances, light is too fast for any biological reaction or dripping water clock. We need a mechanical clock that can slice time into millionths of a second. We enter the 19th century, the era of extreme mechanical engineering. The year is 1849. A French physicist named Hippolyte Fizeau decides he is going to solve Galileo's problem on Earth. He isn't going to use human reaction time. He is going to invent a machine that blinks faster than the human eye can comprehend. Fizeau sets up an experiment in Paris. He needs distance, so he uses the geography of the city. He sets up his light source and his measuring equipment at his father's house in the suburb of Suresnes. He takes a high-quality mirror and he holds it up to the top of the hill of Montmartre. He hires surveyors. They measure the exact straight-line distance from the house to the mirror on the hill. The distance is exactly 8,633 meters, about 8.6 kilometers. So light will leave the house, travel 8.6 kilometers to the mirror, bounce off, and travel 8.6 kilometers back. Total round-trip distance, 17,266 meters. The distance is locked in. Now, Fizeau needs a light source bright enough to be seen from 8 kilometers away through the smog of Paris. He uses a carbon arc lamp, 2 rods of carbon with massive electrical voltage pumping through them, creating a blindingly bright spark. He puts a lens in front of the spark to collimate the light, to focus it into a tight, intense, perfectly straight beam, like a laser pointer. Now comes the genius, the clock. Fizeau takes a brass wheel, a gear. He has a machinist cut exactly 720 teeth into the edge of the wheel. Between every single tooth is an exact, perfectly identical empty gap. 720 teeth, 720 gaps. He mounts this toothed wheel vertically, directly in front of his arc lamp. The beam of light has to pass through the edge of the wheel to get out of the house. He sets up a half-silvered mirror, a piece of glass angled at 45 degrees so he can look through an eyepiece from the side. and see the returning beam of light. Let's walk through the exact mechanics of what happens. Step 1. The wheel is completely stationary. Fizeau rotates it by hand until one of the empty gaps is sitting perfectly in front of the arc lamp. The light shoots out, goes right through the gap, flies 8.6 kilometers to Montmartre, hits the mirror, flies 8.6 kilometers back, goes cleanly through the exact same gap, bounces off the angled glass, and hits Fizeau's eye. Fizeau looks in the eyepiece and sees a bright, steady star of light. Step 2. Fizeau connects the toothed wheel to a clockwork mechanism driven by heavy falling weights like a grandfather clock on steroids. He engages the gears. The wheel starts to spin, slowly at first. Let's slow down time and look at a single pulse of light. There's a gap rotates in front of the lamp. A pulse of light shoots out. The light flies to Montmartre and bounces back. But remember, the wheel is spinning. During the tiny fraction of a second it took the light to make the 17-kilometer round trip, the wheel has physically rotated. The gap has moved forward a tiny bit. The light comes back, and instead of going cleanly through the center of the gap, part of the light beam hits the edge of the advancing brass tooth. Fizeau looks in his eyepiece. The bright star of light starts to flicker and dim. Step 3. Fizeau adds more weight. He cranks the gears. The wheel spins faster and faster. The whirring of the brass is getting loud. He controls the speed very carefully, watching a dial connected to the axle that tells him the exact revolutions per minute, RPM, of the wheel. He keeps increasing the speed until something highly specific, highly dramatic happens. He looks in the eyepiece and the light is gone. Total, absolute darkness. Why did the light disappear? Because Fizeau has perfectly synced the mechanics of the spinning brass with the speed of the light beam. Let's trace it again at this exact speed. The gap is in front of the lamp. A pulse of light escapes. The light travels 17.266 kilometers round trip. In the exact amount of time it took the light to make that trip, the wheel has rotated exactly enough so that the adjacent solid brass tooth has slid perfectly into the position where the gap used to be. The returning light beam smashes dead center into the solid brass tooth. It cannot pass through. It does not reach the eyepiece. Fizeau sees nothing but black. This is a mechanical eclipse happening on a tabletop. Fizeau doesn't need a stopwatch. The wheel is the stopwatch. Let's do the arithmetic. We have to figure out exactly how much time it took for the tooth to replace the gap. Fizeau knows his wheel has 720 teeth and 720 gaps. That means the entire perimeter of the wheel is divided into 1,440 equal segments. To replace a gap with a tooth, the wheel does not need to do a full rotation. It only needs to rotate by one single segment. It needs to rotate exactly 1,440,000th of a complete revolution. Fizeau looks at his RPM dial at the exact moment of total darkness. The wheel is spinning at exactly 12.6 revolutions every single second. If the wheel completes 12.6 full rotations in 1 second, how long does it take to complete just 1,440th of a rotation? You multiply the speed by the segments, 12.6 multiplied by 1,440. The result is 18,144. This means the wheel rotates one segment every 1 over 18,144th of a second. Boom, we have the time. The light took exactly 1/184th of a second to travel 17.266 kilometers. Speed equals distance divided by time, which is the same as distance multiplied by the denominator of the time fraction, 17.266 multiplied by 18,144. Fizeau calculates the speed of light to be 313,274 kilometers per second. For the first time in human history, the speed of light was measured using completely earthly distances and human-built mechanical instruments. Fizeau trapped it. Now Fizeau's number was about 4.5% too high. Now Fizeau's number was about 4.5% too high. Why? Because of human error in observation. How do you judge absolute perfect darkness? As the wheel speeds up, the light gets dimmer and dimmer until it fades to black. But the human eye is not perfectly sensitive. It might look completely dark to Fizeau, a fraction of an RPM, before it is actually perfectly eclipsed. And measuring exactly 8.6 kilometers over the rooftops of Paris in 1849 with chains and transits leaves a little bit of slop in the distance variable, but the physical principle was absolutely flawless. Yet the physicists are still not satisfied. Fizeau's setup was massive. You needed a whole city. You needed clear weather. You needed a giant arc lamp. What if you want to measure the speed of light in a single laboratory room? What if you want to measure the speed of light not in the air, but passing through a dense physical medium, like a block of glass or a massive tube of water? You cannot build a tube of water 8.6 kilometers long. You need a much shorter distance, let's say 20 meters. If you shrink the distance down to 20 meters, the round trip is 40 meters. The time it takes light to travel 40 meters is roughly 0.0000001 second, and 1/10 millionth of a second. Fizeau's toothed wheel cannot measure that. To block light over a 40-meter trip, the wheel would have to spin at an RPM so high that centrifugal force would rip the brass apart into shrapnel. We need an entirely new mechanism, a more elegant, sensitive trap. 1 year later, 1850. Another French genius, Léon Foucault, steps up. Foucault looks at Fizeau's wheel and says, the problem with the wheel is that you're trying to chop the light into discrete blocks. You are looking for a yes/no answer, light or darkness. That is too clumsy. We shouldn't block the light. We should bend it. Foucault gets rid of the wheel. He completely redesigns the experiment using a rotating mirror. This is one of the most beautiful physical experiments ever devised. I want you to pay very close attention to the geometry here. Foucault sets up his experiment inside a single room. Let's trace the equipment. First, the light source. A bright beam of light passes through a slit to make a sharp vertical line of light. This light travels forward and hits a small, perfectly flat mirror. But this mirror is not mounted to a wall. It is mounted on a vertical axle, connected to a high-speed steam-powered air turbine. It can spin freely. When the light hits this flat mirror, it bounces off at an angle. It travels down the length of the room, let's say 20 meters away. At the other end of the room is a stationary mirror. But it is not a flat mirror. It is a concave mirror, curved like a shallow bowl. The concave mirror is ground to a very specific curvature. The radius of the curve is exactly equal to the distance between the two mirrors. Why? Because of a beautiful property of optics. If you put a light source at the center of curvature of a concave mirror, any ray of light that hits the bowl will bounce straight back along the exact same path it came from. So let's trace the light when the flat mirror is completely stationary. The flat mirror happens to be angled correctly. The beam leaves the slit, hits the flat mirror, bounces down the room, hits the concave mirror 20 meters away. Because of the curve, it bounces perfectly straight back, hits the flat mirror again, bounces perfectly straight back toward the slit it came from. Foucault places a beam splitter, a half-silvered glass, in the path near the slit so he can observe this returning beam with a high-powered microscope eyepiece. When the system is stationary, he looks in the microscope and he sees a sharp, bright line of light resting perfectly dead center on a glass crosshair. Now Foucault fires up the steam turbine as the flat mirror starts to spin, fast. Foucault engineered a turbine that could spin the mirror at an astonishing 800 revolutions per second. The edge of the mirror is moving at supersonic speeds. It is screaming. Let's slow down time to a crawl and track a single photon of light. The mirror is spinning rapidly. For a tiny microsecond, it faces the right direction. The light beam hits the flat mirror and bounces toward the concave mirror. The light travels 20 meters down the room. The light hits the concave mirror. The light travels 20 meters back. But here's the trick. During the tiny, microscopic fraction of a second that the light was physically in the air, flying across the room and back, the flat mirror did not stop spinning. It kept rotating. By the time the light gets back from the concave mirror, the flat mirror is no longer at the exact same angle it was when the light left. It is rotated forward by a microscopic angle. Let's call that angle theta. Because the flat mirror has rotated when the returning light hits it, it does not bounce perfectly back to the original slit. It bounces back at a slightly skewed angle. And here's a fundamental rule of optics. If you rotate a mirror by an angle of theta, the reflected beam of light rotates by an angle of exactly 2 times theta. The returning beam is deflected sideways. Foucault looks through his microscope. The bright line of light is no longer sitting perfectly dead center on the crosshair. It is physically shifted to the left by a tiny measurable distance, let's say 0.7 millimeters. Do you see the absolute brilliance of this? Foucault took time, the invisible, untouchable millionth of a second it took light to cross the room, and he converted it into a physical distance. He converted time into a geometric displacement that he could physically measure with a micrometer attached to his microscope. Let's look at the math variables Foucault has. He knows the distance the light traveled to 40 meters total. He knows exactly how fast the mirror is spinning because he has a siren gear attached to the turbine that winds at a specific acoustic pitch. He matches the pitch with a tuning fork, 800 revolutions per second. He measures the physical displacement in the microscope, 0.7 millimeters. Using the focal length of the lenses and the geometry of the setup, he translates that 0.7 millimeter shift into the exact angle the mirror rotated, 2 times theta. If he knows the angle the mirror rotated and he knows how fast the mirror is spinning, he can calculate the exact time it took the mirror to rotate that far. That time is the exact time the light was in the air. Distance divided by time equals the speed of light. Foucault calculates it. In his refined 1862 experiment, using a slightly longer baseline with multiple folding mirrors, he gets a value of 298,000 kilometers per second. He is within 0.6% of the true value. He did it inside a single building. But Foucault didn't stop there. He used this incredible machine to settle the greatest theoretical war in the history of physics. In the 1850s, nobody knew what light actually was. There were 2 warring camps. Camp 1, Isaac Newton, the god of physics. Newton argued that light was made of particles, which he called corpuscles, tiny bullets shooting out of a lamp. Camp 2, Christian Huygens, a brilliant Dutch mathematician. Huygens argued that light was a wave like ripples on a pond, pushing through an invisible medium called the ether. Both theories could explain reflection and refraction, how light bends when it goes into a glass of water, but the mathematics of the 2 theories made 2 completely opposite, mutually exclusive predictions about the speed of light. Newton's particle theory predicted that when light hits a dense medium like water, the gravitational pull of the water molecules accelerates the particles. Therefore, Newton predicted light travels faster in water than in air. Huygens' wave theory predicted that a dense medium creates drag, resisting the oscillation of the wave. Therefore, Huygens predicted light travels slower in water than in air. Nobody could prove who was right, because nobody could measure the speed of light in water until Foucault. Foucault takes his rotating mirror setup. Between the spinning mirror and the stationary concave mirror, he places a massive lead tube, 3 meters long, filled with pure water. The ends of the tube have flat glass windows. Now, the light ray has to fly through 3 meters of air, plunge through 3 meters of water, hit the concave mirror, plunge back through the 3 meters of water, and fly through the air to the spinning mirror. Foucault turns on the steam turbine, 800 revolutions per second. He looks through the microscope. Here is the logic. If Newton is right, and light speeds up in water, the light will complete the round trip faster. It will take less time. Because it took less time, the spinning mirror will have less time to rotate, The angle theta will be smaller. Therefore, the displacement of the dot in the microscope will be smaller than it was in pure air. If Huygens is right and light slows down in water, the light will take longer to make the round trip. The spinning mirror will have more time to rotate. The angle theta will be larger. Therefore, the displacement of the dot in the microscope will be larger than it was in pure air. Foucault looks at the micrometer. The displacement was larger. The light took longer. Light travels slower in water. Newton, the undisputed god of classical mechanics, was fundamentally wrong about the nature of light. In one single, elegant mechanical experiment, Foucault measured the speed of light to under 1% accuracy and destroyed the corpuscular theory of light, proving light operates as a wave. That is how you do experimental physics. But we march forward. The precision must be tighter. The 20th century approaches. The era of American industrial might. Enter Albert A. Michelson. If Foucault was a genius, Michelson was a fanatic. Michelson dedicated his entire existence on Earth to measuring the speed of light. He won the Nobel Prize for it. He wanted to take Foucault's rotating mirror and push the mechanical engineering to the absolute physical limit of human capability. Michelson looks at Foucault's experiment and identifies the primary source of error. Foucault was measuring the tiny lateral displacement of a beam of light in a microscope. It was a fraction of a millimeter. When you are measuring something that small, any vibration from the steam turbine, any thermal expansion of the brass, any slight aberration in the glass lenses ruins your precision. Michelson says, I don't want to measure a tiny angle. I want a null method. A null method in physics means you adjust the machine until the needle reads exactly zero. You adjust the system until the light comes back perfectly to the original spot with absolutely no displacement. How do you do that with a spinning mirror? You don't use a flat mirror. You use a polygon. Imagine a solid block of steel. You machine it into a perfect octagon. 8 perfectly equal sides. You polish those 8 sides until they are perfectly flat, flawless optical mirrors. You mount this octagonal mirror on a steel axle driven by a high-pressure air turbine. Michelson wants distance, huge distance. He is in Southern California in the 1920s. He establishes his primary station at the Mount Wilson Observatory, high up in the San Gabriel Mountains. He establishes a secondary reflection station on Mount San Antonio, Mount Baldy, directly across the valley. The distance is roughly 22 miles, but roughly is totally unacceptable to Michelson. If you want the speed of light to be accurate to a fraction of a percent, the 22-mile distance has to be known to an accuracy of a few millimeters. You cannot use a map. You cannot use standard surveying equipment. Michelson forces the United States Coast and Geodetic Survey to completely reinvent how they measure distance. They send a team of elite surveyors into the rugged California canyon. They use tapes made of invar. Invar is a special nickel-iron alloy that has a coefficient of thermal expansion of nearly zero. It doesn't stretch in the heat of the day, and it doesn't shrink in the cold of the night. They clear a baseline in the valley. They pull the invar tape tight, measuring exactly 50 meters at a time. They measure the tension on the tape with a spring scale to ensure it is pulled exactly the same amount every time. They measure the temperature of the tape to calculate the sag in the middle of the tape caused by gravity. They calculate the curvature of the earth beneath the tape. They drag this tape through the brush, step by step, triangulating the exact distance between the concrete pier on Mount Wilson and the concrete pier on Mount San Antonio. They determine the distance is 35,385.5 meters, with an error margin of literally 1 inch over 22 miles. The total round-trip distance is 70,771 meters. Now the setup. Michelson mounts his octagonal mirror on Mount Wilson. He uses a ridiculously bright carbon arc lamp. The beam of light hits face number 1 of the stationary octagon. It bounces off at an angle, flies 22 miles across the valley floor to Mount San Antonio. It hits a fixed, curved mirror, which bounces it straight back. The light flies 22 miles back to Mount Wilson. It hits face number 3 of the stationary octagon. Face number 3 bounces the light directly into a long telescope. Michelson looks in the telescope. He sees a brilliant point of light, perfect alignment. Now he turns the valve on the compressed air. The steel octagon starts to spin. Just like Fizeau's wheel, the light immediately disappears. Why? Because the light hits face number 1 and flies off to Mount San Antonio. But the octagon is spinning. By the time the light gets back 0.0002 seconds later, face number 3 is no longer there. The octagon has rotated. The returning light hits the mirror at a skewed angle and bounces off into the walls of the room. It does not enter the telescope. Michelson opens the air valve wider. The turbine screams. The octagon spins faster and faster. 200 revolutions per second. 300. 400. He is looking for one extremely specific speed. He wants the octagon to spin so incredibly fast that during the exact time it takes the light to travel 44 miles round trip, the octagon rotates exactly, precisely 1/8 of a turn. Think about the geometry. If the octagon rotates exactly 1/8 of a turn, face number 2 rotates perfectly into the exact physical position where face number 3 used to be. Because all 8 sides are identical, the returning light beam doesn't care that it is a different face. It hits face number 2, which is at the exact correct angle, and it bounces perfectly, flawlessly, straight down the center of the telescope. Michelson watches through the eyepiece. He adjusts the air pressure, tuning the speed. Suddenly, a faint star of light appears in the darkness. He fine-tunes the speed. The light gets blindingly bright and perfectly steady. It stops flickering. He has done it. He has mechanically frozen time by perfectly matching the mechanical rotation of the massive steel block to the transit time of the light beam. The spinning mirror appears completely stationary to the light. Now we need the math. We have the distance of 70,771 meters. We need the exact time. How does Michelson know exactly how fast the mirror is spinning? He uses acoustics. He has an electrically driven tuning fork connected to a stroboscope. The tuning fork is calibrated to vibrate at exactly 528 hertz, 528 times a second. He matches the speed of the spinning mirror to the stroboscope. When the light is steady in the telescope, the octagon is spinning at exactly 528 revolutions every single second. Let's do the arithmetic. If the mirror completes 528 full revolutions in 1 second, how long does one full revolution take? 1 divided by 528 seconds. But the mirror didn't do a full revolution. It did 1/8 of a revolution to swap the faces. How long does 1/8 of a revolution take? 1 divided by 528 multiplied by 8. 528 times 8 is 4,224. It takes exactly 1/4,224th of a second for the mirror to rotate one face. That is 0.0002367 seconds. That is the time the light was in the flight. Speed equals distance divided by time. 70,771 meters divided by 0.000002367 seconds. Michelson published his results in 1926. His value for the speed of light, 299,796 kilometers per second. The true value is 299,792. Michelson was off by 4 kilometers per second. His error margin was 0.001%. It is an achievement of mechanical precision that boggles the mind. But remember what I said. Michelson was a fanatic. He was not satisfied. He looked at his 1926 data and he saw the flaw. The flaw was not the mirrors. The flaw was not the tuning fork. The flaw was the Earth itself. Light was traveling through 44 miles of atmospheric air. Air has density. Air has temperature. Air has humidity. The density of the air in a canyon changes wildly from morning to noon to midnight. When light travels through dense air, it slows down slightly, a tiny fraction of a percent, but it slows down. To get the absolute, true, fundamental speed of light, you must measure it in a perfect vacuum. You must measure it in nothingness. You cannot suck the air out of a 22-mile valley. So what does Michelson do? He is an old man now, in his late 70s. He goes to the Irvine Ranch in flat Southern California. He raises the money and he orders the construction of a steel pipe. Not a little pipe, the massive corrugated steel pipe, 3 feet in diameter and exactly 1 mile long. He lays this mile-long pipe across the flat ranch land. He bolts the sections together. He seals every single joint with thick rubber gaskets and canvas. He connects massive industrial steam-powered vacuum pumps to the pipe. For days, the pumps scream, sucking millions of cubic feet of air out of the steel tube, trying to pull a near-perfect vacuum. The atmospheric pressure outside tries to crush the pipe, but the steel holds. Inside this mile-long vacuum chamber, Michelson sets up his mirrors. He uses a 32-sided spinning mirror now to get even higher precision. Because the tube is only 1 mile long, he puts flat mirrors at both ends, bounces the light beam back and forth 10 times, folding the light path to increase the distance the light travels inside the vacuum. Yet he is incredibly sick. He is dying. He can't even get out of bed to look through the eyepiece. His assistants, Francis Pease and Fred Pearson, have to run the machine and bring the data to his bedside. Michelson dies in 1931 before the experiment is fully completed, but his team finishes the work. In 1932, they published the final result of the mile-long vacuum tube, 299,774 kilometers per second. This is the absolute end of the road for classical mechanics. From Galileo blinking his eyes on a hill, to Romain looking at planetary shadows, to Fizeau's screaming brass teeth, to Foucault's steam-powered flat mirror, to Michelson's mile-long vacuum pipe. We've pushed the physical machining of gears, glass, and steel to the absolute limit, dictated by the atomic structure of the materials themselves. You cannot spin a mirror any faster without centrifugal force, ripping the steel apart into dust. You cannot measure a baseline with an invar tape any more accurately without the quantum vibration of the atoms messing up your ruler. The mechanical era was over. We had trapped light. But science does not stop. In the aftermath of World War II, physics went through a total revolution. We moved from the macro world of moving parts to the invisible world of electromagnetism and quantum mechanics. We realized we didn't need to use visible light anymore. Visible light is just a tiny slice of the electromagnetic spectrum. Radio waves, microwaves, X-rays, visible light. They are all the exact same physical phenomena. They are all oscillating electromagnetic fields, and they all travel at the exact same speed in a vacuum, the speed of light, c. In the 1940s and 50s, our scientists realized that trying to time a wave flying back and forth over miles is the wrong approach. You don't time the flight. You use the geometry of the wave itself. And to Louis Essen, a British physicist, he worked with radar during the war, and he takes a completely different path. He builds a microwave cavity resonator. What is a cavity resonator? Imagine blowing across the top of an empty glass bottle. It makes a tone. The pitch of the tone depends purely on the physical dimensions of the bottle and the speed of sound. If you know the exact dimensions of the bottle and you measure the exact frequency of the tone, you can mathematically calculate the speed of sound. Essen does this for light. He builds a small cylinder out of solid copper. He machines the inside of the cylinder so the dimensions are known to absurd precision, fractions of a micrometer. This copper tube is his bottle. He pumps microwaves into the cylinder. He sweeps the frequency of the microwaves up and down until he hits the exact resonant frequency of the cylinder. When you hit resonance, the microwave bounces back and forth inside the tube, perfectly overlapping itself, creating a standing wave. At resonance, there's a strict mathematical relationship. The speed of the wave equals its frequency, multiplied by its wavelength. Essen knows the frequency. F, as he is generating the microwaves and can measure the electronic oscillation. He knows the wavelength, a lambda, because the standing wave fits perfectly inside his precisely measured copper cylinder. He multiplies the two numbers together. No spinning mirrors, no 22-mile baselines, no vacuum pipes, just pure electromagnetism in a copper cup. Essen calculates the speed of light 299,792.5 kilometers per second. The precision is staggering. We are now counting the individual waves of light. Then, in the 1960s, the ultimate tool is invented, the laser. A laser is a miracle for measuring light. Normal light from a light bulb or a spark is messy. It's a chaotic jumble of different wavelengths overlapping and washing each other out. A laser produces coherent light, a pure, single, continuous wave, one exact color, one exact frequency, marching perfectly in step. In the 1970s, scientists at the National Bureau of Standards in Boulder, Colorado, decide to perform the ultimate measurement. They use a helium neon laser. They use a complex chain of massive atomic clocks, cesium beam clocks, to measure the exact frequency of the laser light. Light waves oscillate incredibly fast, hundreds of trillions of times a second. The atomic clock gives them the exact number. Then they use an interferometer to measure the wavelength of the laser. An interferometer splits the laser beam, bounces it off mirrors, and brings it back together. By carefully moving one mirror and counting the light in dark interference fringes, they can measure the physical length of a single wave of light to the accuracy of an atomic diameter. They have the absolute best measurement of frequency. They have the absolute best measurement of wavelength. They multiply them together. The number they get is breathtaking. 299,792.458 kilometers per second. Or more cleanly, 299,792,458 meters per second. The measurement was so ridiculously precise that the error bars shrunk down to roughly 1 meter per second. But here, physics ran into a catastrophic philosophical wall. The team in Colorado realized they could not make the measurement any more accurate, not because their lasers were bad, not because their atomic clocks were drifting. They hit the limit because of the ruler. Remember, speed is distance divided by time. To give a speed in meters per second, you have to know exactly what a second is, and you have to know exactly what a meter is. The second was strictly defined. 1 second was defined as exactly 9,192,631,770 vibrations of a cesium-133 atom. It is perfectly absolute. But the meter was a complete disaster. Historically, the meter was invented during the French Revolution. They defined it as 1/10,000,000th of the distance from the North Pole to the equator, measured along the meridian passing through Paris. But the Earth is a lumpy squash sphere. You can't measure the Earth perfectly. So they changed it. They manufactured a physical stick, a bar made of platinum and iridium metal, and they put 2 tiny scratches on it. They locked it in a climate-controlled vault in Paris. They declared by international treaty the distance between these 2 scratches at exactly 0 degrees Celsius is exactly 1 meter. Every ruler, every tape measure, every baseline on Earth was calibrated against that metal bar. But look at the physics of a metal bar. Metals are made of atoms. Atoms vibrate. Temperatures fluctuate. The bar sagged slightly under its own weight. But when the scientists in Colorado measured the wavelength of their laser to calculate the speed of light, they had to compare their wavelength to a copy of the metal bar in Paris. They measured the speed of light so accurately that the fuzziness of the scratches on the metal bar became the largest source of error in the entire experiment. The width of the physical scratch on the platinum bar was wider than the error margin of the laser interferometer. We had completely flipped Galileo's problem. Galileo had a ruler, but his clock was too slow. Now our clock was perfect, our trap was perfect, but our ruler was fuzzy. The speed of light was trapped inside the error margins of a metal stick sitting in a basement in France. The physicists looked at this and said, This is intolerable. Einstein had already proven in 1905 with special relativity that the speed of light in a vacuum is not just the speed, it is the absolute fundamental speed limit of the universe. It is the bedrock constant of space and time. It never changes. It is exactly the same for every observer everywhere in the cosmos. A metal bar changes. The speed of light does not. So in 1983, the international scientific community met at the General Conference on Weights and Measures. They did something completely radical. They looked at the long, grueling 300-year history of measuring the speed of light, and they closed the book forever. They voted to redefine the physical universe. They took the incredibly precise number measured by the laser experiments, 299,792,458 meters per second. And they declared, this is no longer a measurement, this is an absolute exact defined constant. The speed of light, denoted by the letter c, is precisely 299,792,458 meters per second, period. No decimal places, no error margins. It is a locked parameter of reality. But wait, if you lock the speed of light, what happens to the meter? You throw the metal bar in the garbage. The meter is no longer a stick. The meter is redefined using the speed of light. The official, legal, scientific definition of 1 meter became the exact distance that light travels in a vacuum in exactly 299,792,458 of a second. Do you see the massive philosophical shift? For 300 years, we used distances to figure out the speed of light. Now we use the speed of light to figure out distances. We no longer measure the speed of light. It is impossible to measure the speed of light today because if you tried to measure it, any error in your equipment just means you are calculating the length of your ruler wrong. The speed of light is the absolute truth. Everything else in the universe bends around it. Think about the journey we just took. It started with a guy standing on a hill in Italy in the dark, waving a piece of wood over a lantern, trying to outrace an invisible ghost. It moved to guys freezing on wooden ships, staring at the shadows of Jupiter to keep from sinking. It moved to geniuses in Paris, machining perfect little brass teeth to chop a beam of light into pieces. It moved to an obsessed man dragging metal tapes across the California desert and spinning steel blocks until they screamed. We took something that humans fundamentally believed was instantaneous, magic, a rigid stick connecting the eye to the sun. We broke it down. We treated it like a physical object. We built elaborate, incredible mechanical cages to trap it. We pushed the physical limits of gears, glass, air, and electromagnetism. We chased it until we caught it. And when we finally caught it, we realized it was the single most perfect thing in the universe. So we took our rulers, we broke them, and we let light measure the universe for us. That is the mechanic. That is the physics. That is how the speed of light was measured. Today's question is, how do electricity and magnets create light? You know that moment. You're sitting in a cafe, you drop a sugar packet on the table, and it slides and skitters until it finds its resting place. Why does it stop there and not somewhere else? That's a small question. Now imagine someone notices 2 other small things on the table. A little static shock when they touch the cup, and a tiny beam of sunlight making dust sparkle. 2 different everyday events, a static zap and a glittering sunbeam. At first glance, they look unrelated, but there's a delicious, almost mischievous truth. If you look at the rules that describe how the static acts and how the light behaves, those rules are really the same family of rules. The math, the way the world moves here, is the very same sort of math that describes both electricity and light. If that doesn't make you sit up and grin, then we're not playing with the right toys. Because you can start from the humblest curiosities. A spark, compass needle, moving when you put a wire nearby, a flash of light, and end at a single idea that pulls them all together. That is what we're going to do. Follow the curiosity. And along the way, we'll discover the intuition behind why electricity and light are not strangers, but members of the same household. Let's begin with the notion of a force that doesn't need touch. You hold a magnet near a paper clip, and the clip flips and jumps, and no strings, no touching, yet something reached out and tugged. We call that something a field. A field is a description of how space itself is arranged, so that if you put a probe into it, the probe feels a force. The probe could be a little charged object or a tiny compass needle. The compass responds to magnetic fields. The charged object responds to electric field. The field is like a landscape. Hills and valleys tell particles what to do when they stroll through. Now imagine putting a charge somewhere, say a small bit of static electricity perched on a comb. That charge creates an electric field. Put a magnet nearby, and you feel another kind of field. Historically, people thought these were separate things. Magnetism and electricity had different stories. But even early experimenters noticed hints of a relation. Run a current through a wire, and a nearby compass moves. If current is a moving charge, moving charges make magnets dance, there is a connection, a whisper of a larger truth. Fields are awkward to picture if you're used to objects bumping and pushing directly. A helpful image, think of the field like a sea of tiny arrows attached to every point in space. These arrows tell you the direction a test object would be pushed if you set it there. For an electric field around a positive charge, arrows point outward like spokes of a wheel. For a magnet, the arrows loop around a bar magnet in closed lines. You can draw them with a pencil on a board, and they make you see the pattern. Attractions, repulsions, loops. Those patterns are the start of a language. Importantly, and this is the part that will later be magical, fields can change with time. Put a charge on a plate and then yank it away. The arrows in the surrounding space don't instantly reconfigure with a snap. They change, they ripple, and that change can move outward. When the field changes, it can carry energy and information. That's the seed of waves. We are used to waves in water or sound in air, things that need a medium to carry them. Light, however, is not like a boat on a lake. It is a ripple of the electromagnetic field itself. Imagine the field as not just arrows, but as a springy, responsive thing, filling space, when you disturb it. By flicking a charge or making a current wiggle, the disturbance does not require a tugboat of air to carry it. The field itself carries the ripple. The pattern of change propagates outward at a definite speed, and that propagation is what we call an electromagnetic wave. This is where the same math idea begins to feel less like a formal identity and more like a practical recognition. The rules for how electric fields change and how magnetic fields change are interlocked. The changing electric field makes a magnetic effect. The changing magnetic effect makes an electric feeling. Imagine pushing a line of dominoes where every falling domino nudges the next. The domino that is a change in the electric field causes a magnetic change somewhere nearby, which in turn nudges electric again. The disturbance sustains itself and marches outward. It's worth pausing to taste some history, because these were not just dry facts, they were surprises. In the 19th century, scientists noticed that electricity made magnetized needles move. A few decades later, another observed that if you move a magnet near a coil of wire, you induce a current. That was Faraday's great discovery. Motion and change could create electricity. What all this suggested was that electric and magnetic phenomena were not isolated curiosities, but scenes in the same play. Then came the astonishing synthesis. Someone realized that if you write down the rules that connect these changing fields, those rules predict something miraculous. Disturbances travel. The velocity of those disturbances turns out to be the same as the speed of light. Suddenly, light, previously studied as rays and color and mirrors, could be viewed as the outward motion of the very fields that haunt circuits and coils. That was a beautiful moment, a kind of unmasking. Light was no longer a separate phenomenon. It was the visible side of electromagnetic change. Stop for a second and picture a region where the electric field is growing stronger and stronger. If you put a little compass there, it won't point to the electric change directly. But the changing electric state induces a curling tendency, which we experience as a magnetic effect. Think of it this way: an electric change sets up a pattern that compels the magnetic field to rotate in a tiny circle. Similarly, when the magnetic field curls or shifts, it creates a push or pull on charges that looks like an electric field. The two are chasing each other, passing energy back and forth as the wave moves forward. To make this less abstract, imagine two people holding opposite ends of a rope. One person gives a twist that creates a small loop in the rope. The loop travels because the rope's tension and the way neighboring parts influence each other cause the loop to propagate. Here, the electric and magnetic fields are the two intertwined aspects of the rope's motion. No single field is enough to carry the whole phenomenon. They trade. That trading, sustained and synchronized, is the wave. If you look at water waves, you can see them go up and down. If you look at electromagnetic waves, the electric part wiggles in some direction, and the magnetic part wiggles perpendicular to that. The picture is tidy. If light moves forward like a marching band, then the electric wiggle is the trumpet player, swaying side to side, and the magnetic wiggle is the trombone player, swaying at right angles. Their motions are coordinated. That's polarization, the orientation of the electric or magnetic oscillations. Polarization matters in glasses, LCDs, and even how plants sense light. It's also a key signature that shows these are real vector fields, arrows that have direction, not just magnitude. When electromagnetic waves pass, they carry energy, shine sunlight into a room, and the energy in those fields can warm a surface, push on a tiny sail, or excite electrons in a solar cell. The fields are not abstract bookkeeping. They have real dynamical effect. Energy in the field is shared between the electric and magnetic parts, sometimes more in one, sometimes in the other. But they trade continuously as the wave moves. You can think of it like a flywheel system where kinetic and potential energies alternate. That is why, for instance, a light wave hitting a metal surface can jiggle electrons and create heat or electrical currents. You might ask, if light and electricity are the same species of thing, what about the electricity in the plugs in your wall? Those are low-frequency electromagnetic fields. In a radio transmitter, currents wiggle at certain frequencies. The fields they create radiate outwards as waves. If you move charges back and forth slowly, they mostly create near fields, localized patterns that fall off quickly with distance. If you wiggle them fast, you can launch true waves that travel far. That's why AM and FM radios, microwaves, and light are all on the same continuum. They're different frequencies of the same electromagnetic phenomena. The human eye samples a very narrow band, the visible band, while the radios sample much lower frequencies and X-rays much higher ones. Yet the underlying language is the same. There were experiments that showed sparks and coils could create waves that behaved like light. They could reflect, refract, interfere, and diffract. Early radio pioneers produced oscillating currents and measured the waves. They noticed interference patterns and other hallmarks of wave behavior. Two sources could make reinforcement in some places and cancellation in others. The fact that these electrically produced waves could interfere following the same rules as light sealed the conceptual identification. They also measured the speed of these waves and found it matched the known speed of light. That numerical match was the clincher. Electricity and magnetism were singing the same tune as light. Contemporary physics likes to emphasize locality. Effects at one place are influenced by nearby causes and transmitted through the field. The idea that a charge only influences another at a distance by instantaneous action felt uncomfortable. The field idea replaces that with a local mechanism. You disturb the field where you are, and the disturbance propagates to where the other object is. That language fits with relativity and the fact that nothing information-wise travels faster than the wave speed. That unity of fields carrying local interactions and those fields being able to propagate as waves, ties together electricity and optics with the rest of modern physics. When light hits something, it may be reflected, transmitted, or absorbed. Absorption means the field gives up its energy to charges and other degrees of freedom in the material. The microscopic story is that the waves shake electrons in atomic bonds. Those get excited, and their energy can be turned into heat or re-radiated as new waves. Sometimes the response is simple and linear. The material's electrons follow the field's wiggles. Sometimes it's nonlinear and complicated, producing harmonics, mixing, or even generating new colors. That's why lasers, nonlinear optics, and modern photonics exist. By controlling how matter responds to fields, we can sculpt waves for new purposes. Because electric and magnetic fields obey a common logic, we can design devices that manipulate both. A simple antenna converts moving charges into waves. A lens directs waves by varying how the material responds to the fields. A polarizer selects the orientation of the electric wiggle. Engineers exploit these properties. Fiber optics guide light like a train on tracks. This is not because light likes tracks, but because the field finds the path of least leakage through the refractive structure. Photodetectors harvest energy from the fields and turn it into electric currents we can use. The universality of the math makes it possible to borrow techniques across domains. The trick in radio engineering sometimes becomes an optical trick when the frequency is scaled up. We have tools today that Faraday and Maxwell could only dream of. We can build cavities where waves bounce 1 billion times, monitor single photons, and map electric fields at nanometer scale. These tools show that the same basic picture holds up even on tiny scales and at high frequencies. The behavior can become richer. Quantum effects emerge, but the classical field description remains astonishingly powerful for many applications. When fields are intense and fast enough, quantum features must be acknowledged. Yet even then, the classical wave viewpoint gives intuition about where energy goes and how waves will behave. Although we promise no heavy equations, it's fair to mention that light also has a particle face, the photon. That idea says when the field gives up energy in small lumps, those lumps behave like particles in some experiment. But don't think of wave and particle as enemies. They're complementary ways of seeing the same entity. In many circumstances, the wave picture is the natural one. Interference, polarization, and lenses all obey the wave's rules. In others, when tiny energy transfers matter, the photon description helps tally how energy is discretely exchanged. The modern synthesis is that the mathematics describing fields also, when treated properly, explains the particle-like aspect. The two descriptions are different windows into the same structure. You might wonder whether it's just a convenience to use similar math for electricity and light, or whether it reflects something deeper. The answer is that the mathematical structure arises because of the way the physical quantities relate to each other locally. Changing electric fields produce curl-like magnetic tendencies and vice versa. That pattern is not an accident. It is a structural relationship that emerges from experiment and is consistent with symmetry and conservation laws. Once you have that structure, the existence of wave solutions is almost inevitable. So the same math is not a quirk, it's a fingerprint of the underlying way nature organizes charges and fields. Here's a little thought exercise. Imagine a tiny loop of wire. Start a current in the loop and hold it steady. The loop acts like a magnetic dipole with field lines looping around it. Now wiggle the current faster and faster. As you increase the wiggle rate, the nearby fields begin to lag and to generate traveling ripples. If you crank the frequency into the radio or optical range, the ripples become waves you can detect far away. The same loop under different time behavior is alternately a magnet and an antenna. The single object, subject to different dynamics in time, displays the continuum between static magnetism and radiated light. That picture makes the unity practical. By changing time dependence, you can morph the phenomenon. One useful distinction is between the near field and the far field. Near the source, fields can be complicated, dominated by the immediate arrangement of charges and currents. Far away, the pattern simplifies into waves whose direction and polarization are evident. Many devices live in the near field, transformers, inductive charges, and some sensors. The far field is what we typically call radiation, the stuff that travels to distant receivers. The same mathematical framework describes both. The character of the solution just depends on distance and frequency. This is a powerful organizational idea. The same rules produce different regimes of behavior, and recognizing which regime you're in helps you choose the right intuition. One remarkable consequence of the field picture is that disturbances don't travel instantaneously. The coupling between electric and magnetic variations carries changes at a finite rate. When Maxwell, or rather the physicists following Faraday's intuition, worked out the consequences, that rate numerically matched the measured speed of light. Later, relativity put the speed of light at the heart of space-time structure. In that view, electromagnetic fields fit neatly into a geometric picture of space and time, with the speed of light acting as the scale that ties the geometry together. Here again, the same mathematical relationships that govern the fields are consistent with the deepest symmetries of nature. Not all media behave the same. Some materials make different frequencies travel at different speeds. We say they're dispersive. That's why prisms separate white light into colors. Different frequencies of the same electromagnetic phenomenon interact with the material differently. The field's math includes the material response as a parameter, and tuning that parameter can produce amazing effects. Modern materials, engineered at tiny scales, can even bend light the other way or create waves that hardly exist outside the structure. The underlying equations remain the same. We just change the coefficients that encode how materials respond, and then astonishing behaviors appear. The recognition that electricity and light are governed by the same mathematics was not only a conceptual triumph, it launched technologies. Radio was possible because currents could be shaped to make waves. Optics advanced when people used the same ideas to design lenses and mirrors. Photonics and fiber optics arose from applying electromagnetic ideas at very high frequencies. Engineering is in large part the practical manipulation of fields to perform work, sense the environment, or transmit information. The universal math enabled cross-pollination. Radio engineers borrowed tools from optics and vice versa, leading to innovations across the spectrum. Measurement drove the theory as much as the theory drove measurement. The early experiments that tabulated how waves behave, reflection, refraction, interference, forced theorists to adopt a unified field description. Later, precision experiments revealed subtler phenomena, dispersion curves, polarization behavior, and the way fields coupled to quantum systems. Each experimental advance refined the way we write the rules and the language we use to describe the coupling between fields and matter. This interplay of experiment and conceptual simplicity is the hallmark of deep physics. If you look beneath the surface, the field structure respects symmetries, invariances that correspond to conservation law. For example, the way fields transform if you rotate your coordinate axis leads to conservation of angular momentum. Other symmetries protect charge conservation and the relationships that allow waves. These underlying symmetries are part of why a single mathematical structure is so powerful. Symmetry restricts what is allowed. The resulting constrained language produces robust predictions across many contexts. Electromagnetic principles work for a single antenna in your hand and for the vast magnetic fields around stars. The scale changes, the parameters change, but the grammar doesn't. That universality is rare and precious in science. It lets us build devices that harness the same rules that govern distant cosmic phenomena. We can study plasma behavior in a lab and get insights relevant to astrophysics. Controlling waves in the lab suggests ways to manipulate signals in communication systems. The same mathematical language acts as a bridge from the microscopic to the astronomical. When we understand that electricity and light are described by one mathematical framework, it tempts us to ask further. What else fits into the same formal language, right? Quantum field theory generalizes the idea treating particles as excitations of underlying fields. Gravity, the odd one out historically, is encoded geometrically in spacetime itself, but much of modern physics seeks unified descriptions. The electromagnetic example is an encouraging model. Disparate phenomena unified by a consistent mathematical structure. That mindset, seek unity through structure, is why the field idea became a cornerstone of 20th century physics. If you have a small coil, a battery, and a little LED, try this. Create a circuit that briefly interrupts the current. That interruption causes a rapid change in the field configuration near the coil, producing a little pulse that can be detected. Now use a simple radio receiver nearby. You'll detect a spike in the radio domain because the field change launches a broad spectrum of waves. The same current in the coil, if oscillated at a steady frequency, will launch waves at that frequency that a receiver tuned to it will pick up. From a single coil and current, you can walk between near-field interactions and far-field radiation. It's a physical way to see how time dependence makes the difference between static action and radiated light. When we say the same math, it doesn't mean everything about electricity and light is identical. Light has frequency and color. It interferes and polarizes. Electricity in circuits involves resistance, capacitance, and inductance with their practical complication. Materials can be lossy, nonlinear, and messy. The point is more subtle and more profound. The underlying dynamical relationships are of the same family, and that gives one conceptual handle to move between domains. So don't flatten away the differences. Use the unity as a tool, but respect the complexity of each regime. In recent decades, researchers have pushed the boundaries of what can be done with fields, metamaterials, artificially structured materials, can make waves do things nature doesn't allow easily, like bending light backward or trapping waves in tiny spaces. Quantum optics has allowed for controlling single photons. We now entangle light with matter and manipulate quantum states for communication and computation. Each of these advances still leans on the common mathematical structure of electromagnetic fields. New technologies often begin as clever ways to shape material response or boundary conditions for the fields. Picture a tiny region where you can tune the responsiveness to electric and magnetic wiggles. In one configuration, the region swallows waves. In another, it reflects them perfectly. In one, it polarizes the field in a certain direction. In another, it converts frequencies. That mental sandbox is what engineers work in every day, by altering the local rules. Without changing the underlying field language, they sculpt global behaviors. It's like composing music using the same notes, but arranging them differently to create infinitely varied symphonies. So why should you care that the same math describes electricity and light? Because it is a model of how deep insight can simplify the world and make it tractable. It's also a practical revelation. It gives us a unified toolkit to invent, measure, and explore. More than that, it is a reminder that close attention to ordinary curiosity, a spark, a compass swing, a flash of light, can uncover laws that reach far beyond the original observation. If you leave with one image, let it be this. The field is the stage. Electric and magnetic wiggles are the actors that take turns and trade energy. Light is the traveling performance that appears when the actors coordinate their routine. That performance is governed by the same grammar that writes the story of currents, antennas, and the tiny shocks you feel after shuffling across the carpet. And now a friendly dare. The next time you see lightning, a radio station, or the blue of a stained glass window, pretend you are listening to a single orchestra. Try to pick out when the electric section is playing and when the magnetic section answers. It's an absurd game, but it sharpens your intuition. The unity we spoke of is not merely a nerdy fact, it's an invitation to pay closer attention to how the world weaves itself together. Here's something to sleep on. If electricity and light are two faces of the same mathematical creature, what else might hide behind the same sort of structure? Gravity resists easy unification, but perhaps there are clever rearrangements, materials, or experiments that make other forces sing in the same choir. If you find a way to coax a stubborn phenomenon into the same pattern, you may have, in a quiet way, created a path toward a new unification. And that is where curiosity leads, from a sugar packet on a table to the architecture of the cosmos. I want you to do something very simple. I want you to look at a lamp in the room or a light bulb, and I want you to reach over to the switch and flip it on. Click, and there it is. The room is full of light. Instant, immediate. It feels simultaneous. Your finger moves, the light appears. There is no gap. There is no waiting. It feels like light is everywhere all at once. For thousands of years, human beings, very smart human beings, much smarter than you and me, they thought that light was instantaneous. They thought the speed of light was infinite. And why wouldn't they? If I throw a rock at you, you see me throw it, you see it coming, and then bonk, it hits you. You can watch it travel. But light, you open your eyes, and the distant mountains are just there. You don't see the image of the mountain traveling toward you. It just seems to exist. But nature is tricky. Nature holds her secrets tight. And usually when our common sense tells us something is obvious, nature is waiting around the corners to hit us with a pie in the face. Because light does travel. It moves. It is a thing. It is a traveler. And the story of how we found that out and why it moves at the speed it does is perhaps the greatest detective story in the history of science. So let's go back. Let's go back to Galileo. Now, Galileo was a man who didn't take anybody's word for anything. If Aristotle said heavy things fall faster, Galileo said, let's throw them off a tower and see. So Galileo, he suspected that light had a speed. But how do you catch something that fast? He came up with an experiment, a very simple, very human experiment. He got two guys with lanterns. He put one guy on a hill. He put the other guy on another hill, maybe a mile away. The plan was this. Guy number one uncovers his lantern. Flash. As soon as guy number two sees the light, he uncovers his lantern. Flashback. Galileo stood there with a timer, well, a pulse beat or a water clock, and he tried to measure the delay. He tried to measure how long it took for the light to go there and come back. And what did he find? Nothing. He found that the light was too fast for his reflexes. The delay was zero. Or at least the delay was so small that it was masked by the time it took for the guys to just move their hand. So Galileo failed, but he was smart in his failure. He didn't say light is infinite. He said, if it has a speed, it is extraordinarily fast. Faster than I can measure on a hilltop. He realized that a mile is nothing to light. A mile is a joke. To catch light, you don't need a bigger hill. You need a bigger laboratory. You need space. And this is where the story gets wonderful. We move to the year 1676. A Danish astronomer named Ole Rømer. Rømer wasn't looking for the speed of light. That's how science works, usually. You are looking for the bathroom and you find a gold mine. Rømer was looking at Jupiter, specifically the moons of Jupiter, Io, the little moon Io. Now, the solar system is a great big clock. It is the most precise clock we have. Now, Io goes around Jupiter, round and round, and every time it goes behind Jupiter, it gets eclipsed. It disappears, and then it comes out the other side. It's regular. Tick-tock, tick-tock, tock. It happens every 42 and a half hours. So Rømer is watching this, and he's writing down the schedule. He's making a timetable. Okay, the next eclipse should happen next Tuesday at 9 p.m. But then something strange happened. When the Earth was close to Jupiter on the same side of the sun, the eclipses happened right on schedule. But 6 months later, When the Earth swung around to the other side of the solar system, moving away from Jupiter, the eclipses started to be late, and they were lagging behind, minutes late. And then as the Earth came back around closer to Jupiter again, the eclipses caught up. They got back on schedule. Now, most people would have said, "Oh, my clock is broken," or "Jupiter is wobbling." But Roma, he had an imagination. He had a physical intuition. He said, "Wait a minute. The moon isn't late. The news is late. Think about that. The news is late." He realized that the light, carrying the image of the moon, the picture of Io coming out from behind Jupiter, it had to cross the gap between Jupiter and Earth. And when Earth is on the far side of the solar system, that gap is bigger. It's an extra 186 million miles or so. The light had to travel that extra distance. And that took time. It took about 16 minutes to cross the width of Earth's orbit. Romer did the math. He divided the distance by the time. And for the first time in human history, we had a number. We knew that light was not magic. It was a messenger. And the messenger had a speed limit. It was fast. Oh, it was terribly fast. But it was finite. And that changes everything. Because if light yet takes time to travel, it means when you look at Jupiter, you're not seeing Jupiter now. You're seeing Jupiter as it was 40 minutes ago. When you look at the sun, you're seeing it 8 minutes ago. If the sun blew up right now, we wouldn't know it for 8 minutes. We'd be sitting here on the beach, happy as clams, while the sun was already dead. You look at the stars, you were looking at ancient history. We are trapped in a bubble of the past. We can never see the now of the universe. We can only see the then. So we found out it moves. But that brings up the next question, the big question. The question that leads to the title of this talk. What is it? What is moving? Is it a stream of particles, like little bullets? Newton thought so. He called them corpuscles. Or is it a wave, like sound, like ripples in a pond? This was the great war of physics for 200 years. The particle guys versus the wave guys didn't. And in the 1800s, it looked like the wave guys had won. We did experiments, the double slit experiment that showed light interfering with itself, wiggling, canceling out. Only waves do that. Bullets don't cancel each other out, they just pile up. So, okay, it's a wave, but a wave of what? If I shout at you, that's a sound wave. What is waving? The air. The molecules of nitrogen and oxygen are compressing and expanding, shoving each other. If I make a wave in the ocean, the water is waving. You see, common sense says, to have a wave, you need a medium. You need stuff to wiggle. You can't have a wave in nothing. That doesn't make sense. A wave is a property of a substance. So the physicists of the 19th century said, okay, light is a wave. It travels through the vacuum of space. But space can't be empty. It must be filled with a fluid. A mere subtle, invisible jelly that fills the entire universe. And they called it the luminiferous ether. The ether. It sounds like something from a fantasy novel. They said this ether was everywhere. It was inside your head. It was between the stars. It was stiffer than steel because light travels so fast. The medium must be very stiff to vibrate that quickly. But it was thinner than air because the planets moved through it without slowing down. It was a magical substance invented to explain the wave. And everybody believed in it. It had to be there. But then came a man named James Clerk Maxwell. Now, Maxwell wasn't looking at light. Not at first. He was looking at electricity and magnetism. Before Maxwell, we knew about electricity. Sparks, batteries, lightning. And we knew about magnets, compasses. But they seemed like two different things. But experiments started to show that you were connected. If you move a magnet near a wire, you create electricity. If you run electricity through a wire, you create a magnet. They were like two sides of the same coin. They were dancing with each other. Maxwell, he sat down and he wrote equations. He tried to describe this dance mathematically. He found that a changing electric field creates a magnetic field. and a changing magnetic field creates an electric field. So imagine this. Imagine you wiggle an electron. Just shake it. That creates a changing electric field. That changing electric field immediately creates a magnetic field next to it. But that magnetic field is changing too. So it creates an electric field next to it, which creates a magnetic field, and so on and so on. The fields pick themselves up by their own bootstraps, and they fly away from the electron. They travel through space, self-propagating. Electricity creating magnetism, magnetism creating electricity, a chain reaction, a wave. Maxwell looked at his equations and he asked, how fast does this wave go? He calculated it based on the strength of magnets and batteries, just pure numbers from the lab, and out of the paper popped a number, 300,000 kilometers per second. Maxwell must have fallen off his chair, because that number was exactly the number Roma and the others had measured for the speed of light. It wasn't a coincidence. Maxwell realized the great truth. Light is an electromagnetic wave. The light you see, the colors of the rainbow, the warmth of the sun, it is just electricity and magnetism vibrating in empty space. And this is where the mystery gets deep, because Maxwell's equation gave us speed, v, the constant. But speeds usually depend on who is looking. If I am on a train going 60 miles an hour and I throw a ball forward at 10 miles an hour, to me the ball is going 10. But to you, standing on the ground, the ball is going 70. 60 plus 10. Velocities add up. That's how the world works. So, physicists thought, okay, light travels at sea through the ether. So if I am in a rocket ship moving through the ether and I shine a flashlight forward, the light should go faster. Or if I move away from the light, it should catch me slower. They built a machine to measure this, the Michelson-Morley experiment, the most famous failed experiment in history. They measured the speed of light in the direction the Earth was moving, and they measured it sideways. They expected a difference. They expected to see the wind of the ether blowing past the Earth, and they found nothing. Zero. No matter which way they pointed the machine, no matter how fast the Earth was moving, the speed of light was exactly the same. It didn't make sense. Imagine you are running down the street at 15 miles an hour, and a car passes you at 30 miles an hour. To you, the car is only going 15 miles an hour faster than you. But nature was saying, no. If you run next to a beam of light, it still passes you at the speed of light. You can chase it in a rocket going 99% the speed of light, and the beam still flies away from you at exactly c. It's as if you were standing still. How can that be? How can a speed be the same for everyone, no matter how fast they are moving? The math was broken. The intuition was broken. The universe was playing a joke on us. And for 20 years, the physicists sweated. They twisted themselves into knots trying to explain it. They said, maybe the rulers shrink when you move. Maybe the clocks slow down. They were getting close. But they were afraid to take the final step. They were afraid to throw away the ether. And then a clerk from the patent office in Bern, Switzerland, picked up his pen. A young man, Albert Einstein. He looked at the problem and he said, what if the experiment isn't wrong? What if our idea of time is wrong? This is the hinge of history. Einstein said, let's assume Maxwell is right. Let's assume the speed of light is constant. It is the law of the universe. V is fixed. If speed is distance divided by time, and if the speed can't change, then the distance and the time must change. Boom. Relativity. To keep the speed of light constant, space itself must squish, and time itself must stretch. If you move fast, your clock ticks slower. Your ruler gets shorter. Not as an illusion, as a physical reality. Why is light so fast? Or rather, why is light the limit? Because light is the speed at which the universe communicates. And to understand why it's a limit, we have to talk about what speed really means. We have to talk about causality. Because it turns out the speed of light isn't really about light at all. Light is just the thing that happens to go as fast as possible. The speed limit, c, is the speed of cause and effect. But I'm getting ahead of myself. Let's stop and think about the why. Why 300,000 kilometers per second? Why not instant? Why not a million? Imagine if the speed of light was infinite. If light was instant, then every event in the universe would happen simultaneously to every observer. You would look at the sky, and you wouldn't see the past. You would see the present. But more than that, if signals could travel instantly, gravity would travel instantly. If the sun disappeared, the Earth would fly out of orbit instantly. It seems nice, tidy, but Einstein showed us that if you can send signals instantly, you can send signals into the past, you break the timeline. If you can go faster than light, there are reference frames, ways of looking at the universe where the effect happens before the cause. You die before you're shot. The glass breaks before you drop it. You answer the phone before it rings. The universe, above all else, seems to want to protect the narrative. It wants to make sure that A happens, then B happens. So there must be a limit. There must be a maximum speed that information can ripple through the fabric of reality. We call it C, and light, because it has no mass, because it carries no baggage, it goes at the limit. It puts the pedal to the metal and goes exactly as fast as the universe allows any information to move. It isn't that light is special, it's that light is lightweight. Literally, it has zero mass. So the question, why is light so fast, is actually the question, why is the universe built with a speed limit? And to answer that, we have to look at what happens when you try to fight it. What happens if you try to push an electron to the speed of light? We do this. We do this every day in accelerators, like the Large Hadron Collider. We take protons and we kick them. We pump energy into them. They go faster, 90% the speed of light. We kick them again, 99%. Kick them again, 99.9%. Kick them again, 99.999999%. We pump enough energy into them to light up a city. And do they reach the speed of light? No. They get closer, but they never touch it. Why? Because of E equals mc squared. Energy and mass are the same thing. When you give energy to an object to make it move, you're actually making it heavier. Well, not heavier in the sense of putting it on a scale, but it gains inertia. It becomes harder to push. The faster it goes, the heavier it gets. So you need more energy to push it faster. But that energy makes it even heavier. It's a vicious cycle. As you approach the speed of light, the mass of the object approaches infinity. To reach the speed of light, you would need infinite energy. And there isn't infinite energy in the universe. So matter, you and me, the spaceships, the protons, we are trapped. We are condemned to live below the speed limit. We can never reach the horizon. But light, photons, they cheat. They have no mass. They start with zero, so they don't have to accelerate. A photon doesn't start at zero and speed up to C. The moment a photon is born, when an atom jiggles and spits it out, it is already going the speed of light, instantaneously. It cannot go slower. If it exists, it moves at C. If you slow it down, it dies. It gets absorbed. So light lives on the edge. It lives on the boundary of reality. And living on that boundary, things get very, very strange for the photon itself. Have you ever wondered, what does the universe look like to a beam of light? If you could ride a photon, what would you experience? This is a thought experiment Einstein had when he was 16 years old. He imagined chasing a light beam. Let's apply what we know about time dilation. We said, the faster you move, the slower time ticks for you. If you go 99% the speed of light, a year for you is 7 years for the Earth. If you go 99.999%, a year for you is 1,000 years for the Earth. Now take it to the limit. If you hit 100%, if you hit C, time stops. Zero. For a photon, time does not pass. It leaves the surface of a star in the Andromeda galaxy. It travels for 2 million years through the void. It hits your eye on a Tuesday night. To us, that trip took 2 million years. To the photon, it was instant. The moment it was born, it hit your eye. The birth and the death, or the same moment. For light, there is no distance. There is no time. The universe is a single point of contact. This is a profound thing to think about. We think of the universe as this vast, lonely place full of empty space. But for the light that connects us, the space doesn't exist. Light stitches the universe together. It brings the news of the stars to us instantly from its perspective. So why is light so fast? Because it is the messenger that transcends time. Because it has stripped away all the weight of matter so that it can show us the structure of space-time itself. So we have this speed limit, 186,000 miles per second, 300,000 kilometers per second. It's a big number to us. But on the scale of the universe, it's actually kind of slow. Think about it. It takes light 100,000 years just to cross our own galaxy. The Milky Way, just one island of stars. If you tried to call someone on the other side of the galaxy, you'd say hello. And 100,000 years later, they'd hear it. Then they'd say hi, and another 100,000 years later, you'd hear it. It's a terrible way to have a conversation. So why is the limit so slow? Why does the universe have such a lack? Well, let's look at what c really is. We call it the speed of light, but that is bad branding. It's false advertising. Light is just the most famous thing that travels at that speed. But gravity travels at that speed too. If the sun vanished, Earth would orbit the empty spot for 8 minutes before flying off. Gluons, the particles that hold the nucleus of the atom together, they travel at that speed. Anything that has no mass travels at c. So c isn't a property of light. It is a property of the fabric of space-time. It is the conversion factor. You know how you can measure distance in inches or in centimeters? And there is a number 2.54 that converts them. Well, Einstein showed us that space and time are the same thing. They are just different directions in the same map. But we measure space in meters, and we measure time in seconds. We use different units because we are biological creatures who perceive them differently. The speed of light, c, is just the exchange rate. It tells you how many meters of space are equal to 1 second of time. And the answer is 300 million meters equals 1 second. That is the ratio of reality. So asking why is light that fast is like asking why are there 100 pennies in a dollar? Because that's the exchange rate. Now, I want to talk about something that really bothers people. They say, okay, I get it. Light is fast, but why can't I go faster? Why can't I build a rocket that pushes harder? If I'm going 99% the speed of light and I fire a thruster, I must go faster. And the answer is, you do, but you don't go faster through space. You go faster through time. Wait. Let me back up. This is the most beautiful idea in relativity. It's called the four velocity. Imagine you are in a car. You can drive north or you can drive east. If you are driving purely north at 60 mph, you are making zero progress east. If you turn the wheel and drive northeast, you are now moving a little bit east, but you've slowed down your progress north. You traded some north speed for east speed. Now Einstein says everything in the universe, you, me, this cup of coffee, we are all moving at the speed of light all the time. But we are moving at the speed of light through space-time, the four-dimensional map. Right now, you are sitting in a chair. You are not moving through space. Your speed in space is zero. So all of your speed is being used to move through time. You are traveling through time at the maximum possible velocity. That's why you're aging. You are hurtling into the future at the speed of light. Now imagine you get in a rocket ship. You start to move through space. You are turning the wheel. You are diverting some of your velocity. You are taking it away from the time direction and putting it into the space direction. So, because you are moving through space, you must move slower through time. That is time dilation. That is why the astronaut ages slower. He isn't experiencing magic. He is just changing his direction in space-time. Now, what happens if you put all your speed into space? You turn the wheel all the way. You use 100% of your velocity for spatial travel. Well, if you use 100% for space, you have 0% left for time. Time stops. And that is what light is. Light is something that has rotated its velocity entirely into the spatial dimension. It has no speed left for time. So you can't go faster than light through space because you can't be more than 100% committed. You can't drive north faster than 60 mph if your car's top speed is 60 mph. You are already maxed out. We are all traveling at CG. Light just happens to do it horizontally while we do it vertically. Doesn't that make you feel a little better? You aren't slow. You are just moving in a different direction than the light beam. You are a time traveler. Now let's get back to the why. Why do we have mass? Why are we stuck in the slow lane? If everything is naturally moving at c, what slows us down? This brings us to the Higgs field, a very modern discovery. Peter Higgs and his friends predicted it in the 1960s, and we found it in 2012. Imagine the universe is filled with a thick syrup, or a room full of people at a cocktail party. This is the Higgs field. It's everywhere. Now, some particles, like the photon, they are like ghosts. They pass through the cocktail party and nobody notices them. They zip through the crowd at top speed. But other particles, like the electron or the quarks that make up your body, they are popular. As they try to move through the room, the people at the party cluster around them. Hey, look, it's an electron. They clump. They interact. They slow it down. This clumping, this resistance is what we call mass. Mass isn't a thing you have. Mass is a measure of how much you interact with the background field of the universe. You are heavy because you're swimming through molasses. If we could turn off the Higgs field, snap instantly, all your atoms would lose their mass. And what would happen? You would explode. Well, not explode like a bomb. You would cease to be solid. All your particles, the electrons, the quarks, they would suddenly accelerate to the speed of light. They would fly apart. You would dissolve into a spray of radiation moving at c. Biology would be impossible. Chemistry would be impossible. Atoms wouldn't hold together. So the reason we are here, the reason we can sit and think and drink coffee, is because we are slow. We are the sluggish ones. We are the ones that got stuck in the syrup. And thank God for that, because complexity needs time. Structure needs stability. If everything was flying around at the speed of light, nothing could ever settle down to build a DNA molecule. Nothing could ever build a brain. The slow lane, the world of mass, is the only place where life can exist. So we shouldn't be jealous of the light. The light is fast, but it is dumb. It can't stop. It can't think. It can't feel. We pay a price for our existence. We are heavy. We are slow. We are trapped in time. But the reward is that we get to be real. We get to be solid. Now, let's talk about what happens when light does interact with matter. Because I said light always travels at c. And that's true in a vacuum, in empty space. But you know that light slows down in glass or in water. That's how lenses work. That's how your eyeglasses work. The light hits the glass and they slows down, bends and focuses. But wait a minute, didn't I just tell you that light can't slow down? That it must go at c? Am I lying to you? No. This is where the atomic picture is important. Imagine the photon entering the glass. The glass is full of atoms, electrons. When the photon comes in, it hits an electron. Look, the electron absorbs the photon. It swallows it. The electron gets excited. It jiggles. It holds on to that energy for a tiny, tiny fraction of a second, a delay, and then it spits it out. It creates a new photon identical to the first one and sends it on its way. That new photon travels at c until it hits the next atom. Oh, absorbed, pause, spat out. So the light between the atoms is traveling at the speed of light, fast, but the process of stopping and shaking hands with every atom along the way, that takes time. It's like a train that goes 200 miles an hour, but it stops at every station. The average speed is slow, even though the train is fast. In diamond, light slows down to less than half its normal speed. Because diamond is a very crowded dance floor, the photons spend a lot of time shaking hands. This is beautiful because it shows that the slowing of light is actually an illusion of the crowd. The individual photons never slow down. They just get distracted. Now, I want to talk about the cosmic implication of this speed. We look at the universe. It is huge. The observable universe is about 93 billion light years across, but the age of the universe is only 13.8 billion years. Wait, how can it be 93 billion light years wide if light only had 13.8 billion years to travel? This is the expansion. Space itself can stretch, and here is the kicker. Space can stretch faster than light. The speed limit c applies to things moving through space. It does not apply to space itself. So right now, there are galaxies on the edge of our vision that are moving away from us faster than the speed of light. The space between us and them is growing so fast that their light can never reach us. It's like running on a treadmill that is going too fast. You run and run, but you move backward. Those galaxies are disappearing. They are falling off the edge of the world. Every day, there are galaxies that cross at that horizon and are lost to us forever. We live in a universe that is slowly deleting its own history. If we lived billions of years in the future, the expansion would be so big that we wouldn't see any other galaxy. We would look up and see only our own star. We would think the Milky Way was the entire universe. We wouldn't know about the Big Bang. We wouldn't know about the expansion. We would be lonely. So we are lucky. We live in the Goldilocks era of the universe. We live at a time when the light can still reach us. We can still read the story of the beginning. Let's go back to the human scale. We use this speed. We use it every day. Your GPS, your phone, it talks to satellites. Those satellites are moving fast, and they are high up in gravity. Because of relativity, the clocks on the satellites tick at a different speed than the clock in your phone. They drift by about 38 microseconds a day. That sounds like nothing. Microseconds. All right. But light travels 300 meters in a microsecond. If we didn't correct for relativity, if we didn't understand Einstein, your GPS would be off by 10 kilometers every day. You would ask for directions to the grocery store, and it would send you to the next town. So these abstract ideas, these things about light speed and time dilation, they are the reason you can order a pizza and have it delivered to your house. It is practical physics, but there is one more thing about light. We talked about it being a wave, but we also said it comes in packets, photons. This is the quantum duality. And there is an experiment, a thought experiment that shows just how weird this speed limit is. It's called quantum entanglement, spooky action at a distance. If I take two photons and I create them together, they can be entangled. They are twinned. They share a wave function. If one is spinning up, the other must be spinning down. Now I send one to you and I keep one. You go to Mars. I measure mine. I find it is up. Instantly yours becomes down. It doesn't matter if you're on Mars or across the galaxy. The moment I know mine, yours is determined. Does this break the speed limit? Did a signal travel from me to you faster than light? It feels like it. It bothered Einstein terribly. He thought it meant quantum mechanics was broken. But it turns out no signal traveled. You can't use this to send a message. You can't use it to send a Morse code because the result is random. I can't force my photon to be up so that yours becomes down. I just measure it and it's random. So you see a random result too. There is a correlation, but no communication. Nature protects the speed limit. She allows a connection faster than light, but she forbids information faster than light. It's a loophole, the secret back channel that the universe uses to keep its books balanced, but it doesn't let us use it to cheat the timeline. We can't send a warning to the path. We can't break causality. The speed limit holds. So I told you, rule. I told you that nothing can go faster than the speed of light. And that is true. In a vacuum, in empty space. But you know, physics is a lot like law. There are the laws of the land, and then there are the local ordinances. What happens if we look inside a material, like water or glass? I told you earlier that light slows down in water. It travels at maybe 75% of its vacuum speed. The photons are busy shaking hands with the water molecules, so the group speed is slower. Now, here's a mischievous question. If light is going slow, can we shoot a particle faster than the light? In a vacuum, the electron can never beat the photon. The photon is the champion. But in water, the photon is handicapped. It is running in mud. The electron, if we shoot it hard enough, can actually go faster than the light wave in that water. It's like a speedboat going faster than the waves it creates. And what happens when a boat goes faster than its own wave? You get a weight, a V shape of water trailing behind it. What happens when a jet plane goes faster than the speed of sound? You get a sonic boom. Crack. The pressure waves pile up. Well, nature is consistent. If an electron travels faster than light in water, it creates a photonic boom, a shock wave of light. We call it Cherenkov radiation. And it is beautiful. If you have ever looked down into a nuclear reactor pool, and I don't recommend you do it without a badge, but if you see a photograph of the core, it is glowing. It has this eerie, ghostly electric blue glow. That blue light, that is the sonic boom of the electrons outrunning the light beams in the water. It is the scream of the particles breaking the local speed limit. So you see, you can go faster than light as long as you pick a race where the light is running slower. But let's go back to the vacuum. Let's go back to the real speed limit. I want to tell you the story of a photon's life, because when we ask why is light so fast, we often forget how hard it works to get to us. Let's look at the sun. We see the sunshine. It feels warm on your face. You think, that light just came from the sun. It took 8 minutes. And that's true. From the surface of the sun to your eye, 8 minutes, a straight shot through empty space. But how long did it take that light to get from the center of the sun to the surface? The sun is a nuclear furnace. Deep inside, hydrogen atoms are smashing together. Fusion. When they smash, they release energy. Gamma rays, high-energy photons. So a photon is born in the core. It is born moving at the speed of light immediately. Boom. But the core of the sun is crowded. It is dense. It is 150 times denser than water. It is a soup of protons and electrons, packed so tight you can't imagine it. So the photon travels for maybe a centimeter, maybe a millimeter, and whack. It hits a proton. It gets absorbed. The proton jiggles. Then it spits the photon back out. But in which direction? Random. It might go forward. It might go backward. It might go sideways. So the photon flies off again. Whack. Hits another electron. Absorbed. Spat out. Random direction. It is the drunkard's walk. Imagine a drunk man trying to leave a bar, but he takes one step, forgets where he is going, spins around and takes another step, spins around. He moves, but he doesn't get anywhere. This poor photon, it is bouncing billions and billions of times. It is trying to escape, but it keeps getting turned around. Do you know how long it takes to travel the radius of the sun? If it could go straight, it would take 2 seconds. 2 seconds. But because of the bouncing, it takes 100,000 years, sometimes 1,000,000 years. Think about that. The light hitting your eye right now, it was created 1,000,000 years ago, before human civilization existed, before the pyramids, before the Ice Age, when that energy has been trapped inside the sun, bouncing around, desperate to get out for 1,000,000 years. And then finally, it reaches the surface. The photosphere, the crowd thins out, the space opens up, and the photon says, free at last, and whoosh, it flies across the vacuum, 8 minutes, and it hits your retina, and its journey is over. It died so you could see the flower in your garden. It's a tragic story, really, but it tells us something important about light. Light is interaction. Light connects things, but it only connects things when it is free to move. And this brings us to the biggest story of all, the story of the whole universe. Let's wind the clock back all the way. 13.8 billion years. The Big Bang. At the very beginning, the universe was hot, unimaginably hot, and dense. It was so hot that atoms couldn't exist. If a proton and an electron tried to hold hands, a photon would come along and smash them apart. No. Too hot. Keep moving. So the universe was a plasma, a soup of charged particles. Now remember what we said about the sun. When you have a soup of charged particles, light cannot travel. It bounces. So for the first 380,000 years of the universe, there was no light. Well, the light was there, but it was trapped. It was a fog, a glowing, opaque fog. If you were there, you wouldn't be able to see your hand in front of your face. The light would scatter off the fog before it reached your eyes. The universe was blind, but the universe was expanding. And as it expanded, it cooled. It cooled down. The temperature dropped. And finally, it hit a magic number, about 3,000 degrees. The temperature of a dull red light bulb. At that temperature, the photon became just weak enough, just gentle enough that they couldn't break the atoms apart anymore. The proton grabbed an electron. Click, hydrogen. And the photon came along and bounced off? No. The neutral atom let the photon pass. Hydrogen is transparent. Suddenly, in a cosmic blink of an eye, the fog lifted. The charged soup became neutral gas, and the light, all that light that had been trapped for 380,000 years, was suddenly free. It flew in straight lines in every direction. The universe became transparent, and that light, the light from the moment of recombination, it is still flying today. It has been flying for 13 billion years. But because the universe has expanded, that light has stretched. It started as hot white light, but the stretching of space pulled it like taffy. It stretched into infrared. Then it stretched into microwave, and it's hitting you right now. If you turn on an old television set, the kind with the rabbit ears antenna, and you tune it to a channel that doesn't exist, you see static, the black and white snow. Shh. About 1% of that static is the cosmic microwave background. You are watching the Big Bang. You are watching the moment the universe turned on the lights. It is everywhere. You can't hide from it. If you went to the deepest cave, if you went to the darkest void between the galaxies, you would still be bathed in this microwave glow. It is the afterimage of creation. And the amazing thing is, it is uniform. It is the same temperature in every direction. If I look left, it's 2.7 Kelvin. If I look right, it's 2.7 Kelvin. This tells us that the early universe was incredibly smooth. It was a perfect fluid, but not perfectly perfect. If we look really, really closely, we see tiny splotches, tiny variation. One spot is 2.70001 Kelvin. Another is 2.69999 Kelvin. Tiny ripples in the density. And thank God for those ripples. Because if the universe was perfectly smooth, gravity would have pulled evenly in all directions. Nothing would have clumped. No stars, no galaxies, no us. Those tiny ripples, those little fluctuations in the microwave lights, they were the seeds. Gravity pulled more on the heavy spots. They grew. They collapsed. They became the galaxies. So when we look at that light, we are looking at our own baby pictures. We are looking at the seeds of the structure of reality. Now, I want to pivot a little bit. We have talked about light as a physical thing, a wave, a particle, a speed limit. But we have to talk about color. Why is the world colorful? Why is the sky blue? Why is the sunset red? Why are leaves green? This is all about the interaction of light with matter. It's about the scattering. Take the sky. Sunlight comes in. It is white light. It contains all the colors. Red, orange, yellow, green, blue, violet. But the atmosphere is made of nitrogen and oxygen molecules, small particle. Now, there is a rule, Rayleigh scattering, that says small particles like to scatter short waves. Blue is a short wave. Red is a long wave, so when the sunlight hits the air, the red light goes straight through. It ignores the air molecules. It drives right past. But the blue light, it hits the molecules and bounces. Ping, ping. It gets scattered in every direction. So when you look up at the sky, away from the sun, what do you see? You see the blue light that has been scattered sideways toward your eye. The sky is lit up with the scattered blue waves, but what happens at sunset? The sun is low on the horizon. The light has to travel through a lot more air to get to you. It's going through the thickest part of the atmosphere for hundreds of miles. By the time the light gets to you, all the blue has been scattered away. It's gone, filtered out. So what is left? The reds, the oranges, the survivors. The sunset is red because the blue got lost along the way. It's just physics. But it produces the most beautiful painting in the world every single night. And what about the green leaf? This is biology making a choice. Plants eat light, photosynthesis. They take the photon and use its energy to break water and make sugar. But they don't eat all the light. Chlorophyll, the magic molecule, it loves red light, and it loves blue light. It eats them up. But green light, it says no thanks. It reflects the green. So when you look at a forest, you are seeing the wasteland. You are seeing the leftovers. The plants are rejecting the greenness, so that's what hits your eye. Now here is a question. Why? Why don't plants eat the green too? Why waste it? The sun puts out plenty of green light. There are theories. Some say that early life of purple bacteria ate the green, so the plants had to evolve to eat the rest. But nature is funny. Sometimes she isn't perfectly efficient. Sometimes she finds a solution that works, and she sticks with it. Good enough is a very important principle in evolution. And our eyes, why do we see this specific spectrum? Why don't we see radio waves? Why don't we see X-ray? Look at water. We evolved in the ocean. We are made of water. Radio waves, water absorbs them. That's how your microwave oven works. It uses radio waves to heat the water in your food. UV rays, water blocks them. But visible light, the colors of the rainbow, water is transparent to them. There is a window in the absorption spectrum of water. So naturally, our ancestors evolved eyes that worked in that window. We see the light that gets through the water. If we evolved on a planet made of methane or silicon, we might see entirely different color. We might see an infrared. So our perception of reality, the fact that we think light is this brightness we see, is purely a biological accident. We are tuned to the frequency of our environment. And this brings me to the idea of the invisible world. Because we only see this tiny sliver, we often forget how much we are missing. If you could see radio waves, the night sky would not be dark. The center of the galaxy is screaming in radio. The black hole at the center, Sagittarius A star, is blazing bright in the radio spectrum. If you could see gamma rays, the sky would be filled with violent bursts, hypernovas exploding. If you could see microwaves, the whole sky would be glowing white from the Big Bang. We walk around thinking the night is dark, but it isn't. The night is bright. We are just wearing sunglasses, very, very dark sunglasses called human eyes. Science allows us to take the glasses off, but we build machines, radio telescopes, X-ray telescopes that let us see the universe in its full glory. And every time we open a new window, every time we look with a new frequency, we find something new. We found pulsars. We found black hole. We found the afterglow of creation, all because we realized that light is more than just what we can see. So we have come a long way. We talked about the speed of light being a constant. We talked about mass being a drag. We talked about the colors of the sunset. But there is one more thing. The thing that keeps me up at night, the death of now. We all have this feeling, this intuitive feeling that now is a universal thing. We feel that right now, at this exact moment, something is happening on Mars. and something is happening in the Andromeda galaxy. We imagine a giant cosmic clock ticking away, synchronizing the whole universe. Tick-tock. Newton believed in this clock, and he thought time was absolute. He thought now was the same for God as it was for man. But Einstein, that troublemaker, he showed us that this is an illusion. If light takes time to travel, and if the speed of light is the same for everyone, then simultaneity is dead. Let me give you an example. A train. I love trains. Physics happens on trains. Imagine you are standing on a platform, and a train goes zooming past you at a significant fraction of the speed of light. Fast. Now imagine two lightning bolts strike. One hits the front of the train, one hits the back. You, standing on the platform, you are exactly in the middle. And the light from the front bolt and the light from the back bolt reach your eyes at the exact same instant. You say, aha, those two lightning strikes were simultaneous. They happened at the same time. Fair enough. But what about the guy on the train? He is sitting in the middle of the train, but he is moving. He is moving toward the front bolt and away from the back bolt. The light from the front bolt has less distance to travel to reach him because he is rushing to meet it. The light from the back has to catch up to him. Since light travels at a constant speed, the light from the front hits him first. The light from the back hits him later. He sees the front strike happen, then a pause, then the back strike. He says, they were not simultaneous. The front one happened first. Now, who is right? Is it you or the guy on the train? Common sense says, well, I am standing on the ground, so I am right. Oh, he is moving, so he is confused. But remember relativity. There is no standing still. The Earth is moving around the sun. The sun is moving around the galaxy. From the train guy's perspective, he is standing still, and you are the one moving backward. So you are both right. For you, the events were simultaneous. For him, they were sequential. This means there is no universal now. Now is a slice of cheese. Bear with me. Imagine the universe is a giant block of cheese. The loaf of bread, the block, universe, length, width, height, and time. You, standing on the platform, you slice the cheese straight down. Your knife is your concept of now. In your slice, the lightning bolts are next to each other. But the guy on the train, because he is moving, he slices the cheese at an angle. His slice includes a bit of your future and a bit of your past. This leads to a terrifying conclusion. If I can move fast enough, I can change the angle of my slice so much that my now includes events that haven't happened to you yet. Or someone in the Andromeda galaxy, if they start walking toward Earth, their now might include next Tuesday on Earth. If they turn around and walk away, their now might include last Friday. This suggests, and this is the hard pill to swallow, that the future is already there. The block of cheese exists. The past, the present, the future. It is all one solid chunk of space-time. The dinosaurs are still there in the past. Your great-grandchildren are already there in the full. We are just spotlight beams, crawling through the block, illuminating one slice at a time and calling it now. We feel like we are changing the future. But physics suggests the script might already be written on the film. And the speed of light? It is the geometry of the block. It is the rule that connects the slices. This brings us to time travel. If the past and future are real, can we go there? Can we build a DeLorean? Well, if you look at the equations, if you go faster than the speed of light, you start to move backward in time. Remember the graph? Space on one axis, time on the other. The speed of light is a 45-degree line. If you go faster than that line, you tilt out of the future cone and into the past cone. So if I could build a ship that goes 2 times light speed, I could fly out to a star, turn around, and come back before I left. I could kill my own grandfather. I don't know why physics students are always so violent with their grandparents, but that's the example. If I killed my grandfather before I was born, then I never exist. So I never built the ship. So I never killed him. So I do exist. Paradox. The universe hates paradoxes. It hates logical contradiction. And this is the strongest argument for why the speed limit is absolute. The speed of light is the causality protection speed. It prevents the universe from eating its own tail. It ensures that the cause always comes before the effect. If you break the speed limit, you break logic, and the universe seems to value logic above all else. So you can't go faster than light, not because the engine isn't strong enough, but because it would break the story. But I want to end on a note of unity, because this speed, this C, it did something wonderful for physics. It united things that we thought were separate. Before Einstein, we had energy, and we had math. Two different books, but C tied them together. I know E equals mc squared. Energy is mass times the speed of light squared. Mass is just frozen energy. You are made of frozen light. The atoms in your body, the protons, most of their mass comes from the energy of the quarks zipping around inside. You are a container of energy. And before Maxwell, we had electricity and magnetism. Relativity showed us they are the same thing. Think about a wire, a copper wire with current flowing. The electrons are moving. If you put a compass next to it, the needle moves. Magnetic field. But why? Well, imagine you are an electron moving along with the current. To you, the electrons in the wire are standing still. But the protons in the wire, the metal itself, are moving backward. Because of relativity, the space between the moving protons shrinks. Length contraction. So the wire looks positively charged to you. It pushes you away. That push, that electric repulsion caused by relativity, is what we call magnetism. Magnetism is just electricity plus relativity. It is all one thing. Space and time, energy and mass, electricity and magnetism. They are all facets of the same jewel. And the speed of light is the refractive index of that jewel. It is the constant that ties the universe together into a single, coherent picture. So why is light so fast? It is fast because it is weightless. It is fast because it is the messenger of reality. It is fast because it is the boundary of the present moment. But mostly it is fast so that we can be here. If light were instantaneous, there would be no past, no future, just a chaotic instant. If light were slower, the universe would be dark and cold, unable to communicate. It is exactly the speed it needs to be to allow for a universe that has structure, history, and meaning. And we, us humans, we are the lucky ones who get to sit in the middle of it. We are slow. We are heavy. We are stuck on a rock. But we have minds that can race at the speed of light. We can look at a photon that has traveled for 1 billion years and understand its story. We can capture the light in our telescopes, in our cameras, in our eyes. And in doing so, we verify our existence. We are the universe looking at itself, using the light as a mirror. So the next time you look at the stars, or the next time you just flip a switch in your living room, don't just take it for granted. Think about that messenger. Think about that photon. Think about the 1,000,000-year journey it took to escape the sun. Think about the 8 minutes of freedom in the void. And think about the fact that it ended its journey on your retina just so you could see. It's a gift. Keep looking. Keep wondering. And remember, nature has a great imagination. She is